Hello there, and welcome to Science for Sleep, where curiosity gets cosy and science winds down beside you, like a quiet friend at the end of a long day. Tonight we're setting off on a gentle expedition across something vast, quiet, and seemingly unreachable. Not with a spaceship or a suitcase, not even with shoes, just with the soft hum of wonder and the slow turning of thoughts beneath the stars. Have you ever looked up and wondered if it's truly possible to go there? Not just to the moon or to Mars, but across the entire universe. To leap between galaxies, to step across the void, to somehow leave this little corner of space and find yourself somewhere utterly alien and unimaginably distant. It's the kind of thought that slips in when things go still, when the room dims and the world quiets down enough to hear your own questions echo. Before we begin, I'd love to know where in the world you're listening from. Maybe you're in bed, curled up with a blanket. Maybe you're lying back in a chair with the day slowly melting behind you. And what time is it there? Is it evening with the last golden light catching the windows, or has the night fully arrived, tucking in the world with street lamp shadows and hushed breezes? If you find this little journey soothing or gently fascinating, it would mean the world if you gave the video a like or maybe subscribed. It helps this quiet corner of calm find others who might need a little rest, a little curiosity, and maybe a few answers that arrive not with fanfare but with a whisper. Now, take a breath. Let your shoulders soften. Set aside the noise of the day, the weight of to-do lists and notifications. Because what we're exploring tonight isn't urgent. It's slow and wide and unhurried. The question we're asking is simple. Can you really travel across the universe? When we think of travel, the usual rules come to mind. You go somewhere. You leave point A and arrive at point B. There's motion involved, engines, planning, time. You might take a road, a flight, or even a hike through woods and hills, but space doesn't play by the same rules. Once you zoom out far enough, even defining somewhere starts to wobble. The Earth is already moving, the galaxy is swirling, and the universe itself is expanding while we sit here, quietly breathing. But the question persists. Can we, or anything, travel across the entire universe? To begin answering that, we first have to understand what it means to go somewhere in a universe that's not still, that's not small, that doesn't even have a clear edge. Because what we often imagine as space, that blackness with stars sprinkled across it, isn't an empty canvas waiting to be crossed. It's more like an ever-stretching fabric, a dynamic structure that bends, swells and moves in ways that don't quite match the maps and highways we're used to. The distances involved aren't just big, they're beyond what we're built to grasp. When you hear something like a light year, maybe it just sounds like a poetic way of saying far. But it's a real measurement. A light year is the distance light travels in 1 Earth year. That's about 9.46 trillion kilometres, or roughly 5.88 trillion miles. That's just 1 light year. The nearest star system, Alpha Centauri, is about 4.37 light years away. And that's still in our immediate cosmic neighbourhood. Our own galaxy, the Milky Way, is about 100,000 light years across. If light left one side of it today, it wouldn't reach the other side until long after entire civilizations had risen and fallen here on Earth. That's just our galaxy, and beyond it are billions of others. So when someone asks, can we travel across the universe? It's worth pausing to really feel the scale of what they're asking. This isn't just a question of engines or fuel. It's a question of physics, of whether the universe even allows for such a journey in principle, regardless of how advanced our technology might one day become. What we call the observable universe, the part we can actually see or detect, stretches about 93 billion light years across. That's because the universe has been expanding since the Big Bang, and light from distant regions has been travelling toward us ever since. But even that massive bubble is just what we can observe. The actual universe might be vastly bigger, possibly infinite. And if it is infinite, then crossing it becomes not just unlikely, but undefined. Because how do you cross something with no edge? Still, the curiosity remains. What does it take to move from one end of that observable universe to the other? Could we send something, or someone, all the way? What barriers are in place? Is it simply a matter of speed and time, or is there something deeper baked into the laws of nature that prevents us? To even begin answering that, we need to start small. Not small in size, but small in terms of scope. Not the whole universe, but just a single beam of light. Because light is in many ways the fastest thing we know. Nothing moves faster. According to everything we understand about physics, particularly Einstein's theory of special relativity, the speed of light in a vacuum is the universal speed limit. You can't go faster. In fact, the very fabric of space-time is structured around that limit. So if we're looking to see what's possible, we start by asking, what would it take for light to cross the universe? Let's imagine a photon, a single particle of light, being emitted from one side of the observable universe. It's moving at 209.99 to 792 kilometers per second. That's over 670 million miles per hour. At that speed, it would take about 46.5 billion years to reach us, assuming the universe wasn't expanding during that time. But the universe is expanding, and that changes everything. You see, the space between galaxies isn't static, it's stretching. The fabric of space itself grows over time, and that means objects can move away from each other without actually moving through space. The space between them is what's expanding. This has profound consequences for travel. It means that even if you were to move at the speed of light, the destination itself could be moving away from you faster than you can reach it. This is part of what defines the limits of the observable universe. There are regions beyond which light hasn't had time to reach us yet, and possibly never will, because the space in between is expanding too fast. That expansion isn't like the motion of a car or a rocket. It's the motion of the backdrop itself, the very coordinates that define position. So even light can't catch up, not because it's too slow, but because the finish line keeps retreating faster than it can run. This is one of the quiet heartbreaks of cosmology. There are galaxies out there right now that we will never see. Their light will never reach us, not because we lack the tools or the patience, but because the universe itself has drawn a curtain across them, using expansion as its thread. So where does that leave us? If light can't cross to certain parts of the universe, what hope do we have? Well, that depends on how you define travel. If we're talking about conventional motion, moving a ship or a person through space, then we quickly run into serious problems. First, the energy required to approach the speed of light becomes enormous. The closer you get to that limit, the more mass you effectively have, and the more energy you need to keep accelerating. It's an asymptotic problem. You never actually reach light speed, and you use more and more energy just to gain smaller and smaller increases in speed. But even if we could somehow get past that, even if we had the power to propel a craft at 97% the speed of light, the journey across the universe would still take billions of years, from the perspective of someone watching from Earth. Inside the ship, time would move differently. Thanks to time dilation, the traveller might experience only a few decades or less, but everyone they knew back home would be long gone by the time they arrived anywhere useful. And when they got there, what they found might not be reachable anymore anyway, because the universe might have expanded further in the meantime. There's another problem too. Space isn't empty. At high enough speeds, even a single atom of hydrogen, which is common in interstellar space, becomes a dangerous projectile. At near-light speeds, the sparse particles floating between stars can damage or destroy a craft, simply because of the extreme energy of the collisions. So it's not just a matter of distance. It's not just about how fast you can go. It's about whether the structure of the universe allows for that kind of motion at all. Still, that's not the end of the story. There are ideas, speculative ones, yes, that imagine different ways of getting from here to there without going the usual route. These ideas don't rely on speeding through space, but on reshaping it. Because if space can stretch, maybe it can also bend, maybe it can fold, and that's where things start to get more interesting. If space can stretch, maybe it can also bend. That's the thought that quietly takes hold once you stop thinking of space as an empty container and start seeing it as something with properties. Not just a stage where the universe plays out, but an active participant. If that's true, then distance becomes something more slippery than we usually imagine. On Earth, distance is easy to grasp. You walk a mile, you drive 10 kilometres, you fly across a continent. The idea is simple because the space itself feels fixed. Roads don't expand while you're driving on them. The ocean doesn't swell under your boat mid-voyage. But in the universe at large, the very thing we're trying to cross is itself changing, sometimes in quiet, almost invisible ways. And that leads to a strange question. What does distance even mean when space itself isn't fixed? When the map shifts while you're holding it? To understand this better, imagine standing at one point in space and wanting to reach another at, say, 2 galaxies separated by 1 billion light years. You might think of the distance between them as a straight line, the shortest possible route. But in cosmology, that line doesn't stay the same. The space in between is expanding. So while the galaxies themselves might not be moving through space very much, they're still getting farther apart because the fabric between them is stretching. That means even if you had a ship that could travel unimaginably fast, the destination would still be moving away. The speed of that separation isn't limited by the speed of light, because it's not the galaxies moving through space, it's the space itself expanding. This is one of those quiet details that changes everything. In regions of space far enough away, the expansion of the universe makes those galaxies recede from us faster than light can travel. And so, we lose sight of them, not because of a cloud or a shadow, but because their light can't ever reach us. They're slipping over a cosmic horizon. Now you might wonder how that's even allowed. If nothing can travel faster than light, how can galaxies be moving away from us at faster than light speeds? The key is understanding that it's not their motion that's breaking the rule. It's the expansion of space itself, and that expansion doesn't follow the same speed limits. It's not that objects are racing through space faster than light. It's that the space in between them and us is growing, and the speed of that growth can exceed light's ability to keep up. That's why distance gets so complicated once you step beyond the neighbourhood of stars and start thinking on truly cosmic scales. Because the farther you go, the less stable the concept becomes. It's like trying to measure the distance between 2 points on a balloon while the balloon is being inflated. You can measure the length of the surface at one moment, but as soon as the balloon grows, the measurement changes. The points themselves haven't moved, but the distance between them has grown. And that's exactly what happens across the universe. This changing distance doesn't just affect travel, it affects observation. When astronomers look at very distant galaxies, they aren't seeing them as they are now. They're seeing them as they were billions of years ago. And the light from those galaxies has been stretched along the way. Not just delayed, but physically stretched, increasing its wavelength. That's what we call redshift. It's not just a colour shift, it's a measurement of how much the universe has expanded since the light began its journey. Some of the light we see today left its source when the Earth hadn't yet formed. Some of it began travelling when the first galaxies were still taking shape. We're not seeing the universe as it is, but as it was, a patchwork of ancient light arriving from different moments in time. And because the space in between has expanded, those galaxies are now much farther away than they were when the light was emitted. So the current distance to a galaxy might be much greater than the travel time of its light would suggest. This is one of the reasons astronomers talk about different kinds of distance. There's proper distance, the actual separation at a given moment in cosmic time. There's co-moving distance, which accounts for the expansion of space. There's light travel time, how long the light took to get here, and each one tells you something slightly different about what you're seeing and how far away it really is. All of this makes the idea of travelling across the universe more complicated than just building a faster ship. Because there's no fixed route to chart, no stable roads to follow. The very thing you're trying to cross is in motion, and not in a way that you can easily predict or avoid. It also raises questions about goals. If we say we want to travel to another galaxy, we have to ask what we mean by that. Do we want to go to where that galaxy was when we saw its light? Or where it is now? Because those are two very different places and they're getting more different every second. And then there's the scale. The Milky Way alone is home to perhaps 100 billion stars. Each of those stars may have planets. Many of them are too far for us to ever reach, even with our most ambitious ideas. And yet, that's just one galaxy. There are hundreds of billions more. The total number of stars in the observable universe is so large it's almost meaningless. Trillions upon trillions. More stars than grains of sand on all the beaches of Earth. To travel across that expanse, you'd need more than propulsion. You'd need a completely different way of thinking about space, time, and movement. That's where the idea of bending space comes in. If we can't go faster than light, maybe we can cheat in another way. Not by speeding up, but by shortening the path. In the balloon analogy, if 2 points are far apart along the surface, maybe you could press the balloon together and make those points touch. Then all you'd have to do is step across. That's the basic idea behind things like wormholes and warp drives. They don't break the speed limit, they just try to rewrite the route. But even those ideas run into problems. Because space isn't just flexible, it's also stubborn. It resists being folded or compressed without a fight. You can't just pinch the universe and expect it to behave. It takes energy, lots of it. And in most cases, the kind of energy we'd need doesn't exist in any usable form, or might not exist at all. There's also the question of stability. Even if you could create a shortcut through space, how do you stop it from collapsing the moment you try to use it? How do you make it traversable? How do you protect anything travelling through it from the extreme conditions inside? These aren't just engineering problems, they're questions about the nature of reality, whether space and time can be manipulated in the ways we imagine, whether the equations allow for it, and even if they do, whether those solutions are physically meaningful or just mathematical curiosities that don't correspond to anything real. At the moment we don't know. We have theories, equations, hypothetical constructs, but we don't have evidence. No wormhole has ever been observed. No warp bubble has ever been created. They remain, for now, in the realm of possibility. Not impossibility, but possibility without confirmation. That doesn't mean the idea is worthless. Sometimes, thinking about impossible things teaches us what's possible. It pushes the boundaries of understanding. It reveals the edges of what we know and the shape of what we don't. In the meantime, distance continues to be a moving target, one that resists being pinned down, and that makes the idea of crossing the universe something more subtle than a road trip on a cosmic scale. It becomes a question about definitions. What does it mean to cross something that's always changing shape? What does it mean to arrive when the destination is moving? In some ways, the most we can do, at least for now, is observe, to send out instruments, telescopes, and signals, to watch the light from distant corners of the sky, and in doing so, we learn not just about what's out there, but about the limits of how we can know it, about the tools we use to define motion and distance, and the way those tools sometimes come up short. There's something quietly humbling about that. The universe isn't made to be easy. It's not built for our convenience, but it is built in a way that we can slowly, patiently, begin to understand. Not all at once, not completely, but enough to glimpse the patterns and possibilities, enough to ask the next question. Because if going across the universe the usual way seems impossible, maybe there's another way. A way that involves folding, bending, or slipping between. A way that bypasses distance altogether. And that brings us to something light can't do. Something even photons, for all their speed, can't accomplish on their own. The question of whether space itself can be shaped to allow travel not through it, but around it, as if the universe could be persuaded to hold its breath and let something pass through. If folding or bypassing space is even a remote possibility, the next natural step is to understand what kind of space we're actually dealing with. Not just how it behaves or what's inside it, but how big it truly is. That word, big, is simple on the surface. We use it every day. A big room, a big city, a big number on a bill we didn't expect. But when we ask how big the universe is, we leave that familiar version of big behind completely. We step into something that no longer has a relatable scale, and we find that even the question itself isn't easy to answer. To begin with, there's the part of the universe we can see. Not with our eyes directly, of course, but with our telescopes, instruments, and detectors. This is what we call the observable universe, the bubble of space around us that light has had time to reach from since the beginning. That limit is set not by how far things are, but by how long the universe has existed. Because no matter how fast light travels, it still needs time to get here. And there's only been so much time. The universe is about 13.8 billion years old. So you might assume the farthest we can see is 13.8 billion light years away. But that's not quite right. Because space has been expanding the whole time. That means the light that reaches us today from the earliest galaxies left those galaxies when they were much closer to us than they are now. While that light was in transit, the space it was crossing stretched out. So the galaxies it came from are now much farther away than 13.8 billion light years. Taking that expansion into account, the edge of the observable universe is actually about 46.5 billion light years away in every direction. That gives us a sphere with a diameter of about 93 billion light years. That's the current size of the observable universe. Not the whole universe, just the part we can, in principle, observe. Everything outside that sphere is currently unreachable, not because it doesn't exist, but because its light hasn't had time to reach us, and possibly never will. Those regions are still part of the universe. They're just beyond our horizon, like the parts of Earth you can't see from where you're standing. But unlike the Earth, this horizon isn't something you can travel to. It's a limit set by the speed of light and the expansion of space. It's not a wall, but a boundary of time and motion. So that's one version of the answer. The universe is at least 93 billion light years across based on what we can see. But most cosmologists believe that's only the beginning. There's good reason to think that the universe is much larger, possibly infinitely large. And if it is infinite, then any talk of size becomes more philosophical than physical. Because infinite doesn't mean really big. It means unbounded. No edge, no centre, no measurable total. Just more. Always more. No matter how far you go. Still, infinity isn't something science accepts lightly. It's a mathematical concept, not a measurement. And when we apply it to the physical universe, we're doing so based on what the data suggests, not what we've seen directly. So far, all the observations of the universe's shape and structure, things like the cosmic microwave background radiation and the distribution of galaxies, suggest that the universe is flat, not curved, not like a sphere and not like a saddle, just flat on the larger scales we can measure. A flat universe implies something interesting. It suggests that the universe either goes on forever, or at least extends far beyond what we can see. Because if it were closed, like the surface of a sphere, we'd expect to see signs of curvature in the way distant light behaves, and we don't. So the working assumption, for now, is that the universe is at least much larger than the observable part, possibly infinitely larger. That's difficult to picture, and it raises more questions than it answers. For instance, if the universe is infinite, does that mean there are infinite stars, infinite galaxies, infinite versions of Earth? What does infinite even mean when applied to real things? Let's pause and look at it this way. Imagine standing on a flat, empty plain that stretches to the horizon in every direction. As far as you can see, the ground is level. No hills, no edges, no boundaries. Now imagine the horizon as just the limit of your vision, not an actual edge. The plain might go on much farther, maybe forever. That's a little like the observable universe. It's the part we can access, but not necessarily the whole thing. We might be seeing just a tiny patch of a much larger endless terrain. Of course, we can't be sure. The universe might be infinite, or it might be finite, but so large that the curve is too gentle for us to detect. Like standing in a huge circle and thinking it's a straight line because the arc is too wide to see. Either way, the numbers involved are staggering. Even if the universe isn't infinite, it's still larger than we can travel across by any known method. Not just larger than our technology allows, but larger than physics seems to allow. And yet, we've mapped some of it. Through careful observation, using light, radiation and motion, we've built detailed models of the early universe, the way galaxies cluster, and the overall geometry of space. We've even mapped the cosmic microwave background, the faint afterglow of the Big Bang, which shows us what the universe looked like when it was only about 380,000 years old. That light has been travelling toward us for over 13 billion years, and it gives us a picture not of stars or galaxies, but of the very first patterns, ripples of temperature and density that would eventually form the large-scale structure we see today. From that data, scientists can estimate the total contents of the universe, not just the visible matter, stars, gas, dust, but also the dark matter and dark energy that make up most of the cosmic inventory. According to the latest measurements, ordinary matter, the stuff we can see and touch, makes up only about 5% of the total. Around 27% is dark matter, invisible, mysterious, detectable only through its gravitational effects, and the remaining 68% is dark energy, a force driving the accelerated expansion of the universe. All of this matters because it tells us what kind of universe we live in. The composition and structure determine how space evolves, how it expands, and what its ultimate fate might be. A universe dominated by dark energy, like ours, is expected to keep expanding forever, possibly at an accelerating rate. That means the space between galaxies will continue to grow. Eventually, more and more galaxies will slip beyond our observable horizon, not because they've gone somewhere, but because the space between us has stretched too far. That paints a lonely picture of the far future, a universe where only the closest galaxies remain visible, where most of the cosmos has vanished beyond reach, not through motion, but through expansion. That's what we mean when we say the universe is big. Not just that it's wide or full, but that it contains distances so vast and changes so gradual that we only notice them when we look across billions of years. Even the light we receive from our nearest large galaxy neighbour, Andromeda, has been travelling for over 2 million years. When that light began its journey, early humans hadn't yet walked upright. Civilizations, languages, even continents as we know them, had not yet formed. That's how big the universe is. Big in space, yes, but also in time. Every observation is a look into the past. Every photon is a story from an earlier chapter. So when we ask how big the universe is, we're really asking several things at once. How far can we see? How far can we reach? How far does it go? The answers to those questions don't always line up. We can see 46.5 billion light-years in each direction. We can reach far less, and the universe may go on forever beyond that, or not. We don't know. What we do know is this: the more we observe, the more we realise how much lies beyond what we can touch, and how much of what we thought was empty space is actually alive with structure, motion, and subtle forces. Distance in this context isn't just a number, it's a limit on what we can know, a boundary drawn not by walls, but by light, time, and the laws of physics. And yet, despite all that, we keep looking, we keep asking, not because we expect to cross the whole universe, but because understanding its size helps us understand where we are within it. It shows us the scale of our surroundings and the rules that govern them, and sometimes, just sometimes, it reveals small cracks in those rules, possibilities we hadn't considered, ideas that might one day shift the conversation from what we can see to what we can do. Because if space is this big, and time is this deep, then the challenge isn't just reaching another galaxy, It's finding a way to think about movement and location in a universe that refuses to stay still. Not a flat map with clear routes, but a shifting sea where the stars are never in quite the same place twice. If the universe is too big to reach by ordinary means, and if space itself stretches and shifts beneath any attempt to cross it, then the only thing that ever really seems to travel across these cosmic distances is light. Not people, not ships, not signals in the usual sense. Just light, moving steadily, quietly, across the emptiest stretches of space. That makes light more than just illumination. It's our connection to everything beyond our reach. Every image we have of a galaxy, a star or a cloud of gas halfway across the sky, is built from tiny packets of light, photons, crossing the void for millions or billions of years before finally reaching us, each one carrying a message, not written in words but in energy and colour and direction. We call light the fastest thing in the universe because in a vacuum nothing moves faster. It's not just a record holder, it's the limit. According to everything we know from relativity, the speed of light, about 292 kilometers per second, isn't just how fast light moves, it's how fast anything can move. More than that, it's the speed at which cause and effect can operate. Information, energy, motion, nothing gets ahead of that boundary. It defines what can be seen, what can be influenced, what can be connected. But being the fastest doesn't mean being fast enough. Not on these scales. When light leaves a distant star, it travels with perfect loyalty. It doesn't rest, slow down, or stop for anything. And yet, it still takes its time. Because space is vast, and even something moving at nearly 300,000 kilometers per second still has to cover incredible distances. So it becomes a kind of courier. Not one that we can send back and forth quickly, but one that delivers stories long after they've been written. Imagine, for example, a galaxy 10 billion light-years away. The light from that galaxy began its journey 10 billion years ago. That means we're not seeing it as it is now, but as it was when the universe was less than 4 billion years old. Whatever changes have happened there since, supernovae, new stars forming, black holes colliding, we won't know about them for a very long time, if ever, because the updated light hasn't arrived yet. This delay isn't just a curiosity, it defines how we explore the cosmos. We're not looking at the present, we're looking at a timeline spread out across the sky. Nearer objects show us recent events, farther ones show us the deep past, and the oldest light of all, the cosmic microwave background, shows us what the universe looked like before there were even stars. A glowing fog of hot plasma, cooling and expanding. That background isn't something we see with our eyes, it's microwave radiation, far below visible light in the electromagnetic spectrum. But it's there, all around us, in every direction, like a memory the universe never forgot. And it's smooth, almost perfectly uniform, with tiny ripples of temperature that would eventually grow into galaxies, clusters, and the web of matter we now see. That light is the oldest message we've received. It's the limit of what we can observe directly. Not because nothing existed before that, but because before that time, about 380,000 years after the Big Bang, the universe was opaque, too hot, too dense. Light couldn't travel freely. Photons bounced around in a soup of particles, unable to escape. Only after things cooled did light begin to move in straight lines, and the ones that happened to head our way have been travelling ever since. This means that light is both a probe and a boundary. It shows us what's out there, but it also sets the edge of what we can know. We can't see beyond that surface of last scattering, the moment the universe became transparent, because no light from earlier times has made it to us. And as light travels, it changes. Not because it slows down or gets tired, but because space itself stretches while it moves. That stretch pulls on the light's wavelength, increasing it. Short wavelengths become longer. Blue shifts to red. Infrared shifts to microwave. This is cosmic redshift. and it's one of the clearest signs that the universe is expanding. The farther away a galaxy is, the more its light has been redshifted. That gives astronomers a kind of ruler. By measuring the redshift of a galaxy's light, they can estimate how far away it is and how fast the space between us and that galaxy has expanded since the light left. It's not a perfect map, because the expansion rate has changed over time, but it's enough to build a picture, a three-dimensional view of the universe's structure, depth, and motion. And all of it comes from light, not from direct contact or visits or probes, but from beams of energy travelling through space with perfect patience. There's a strange kind of intimacy in that. Light lets us see things we'll never touch. It brings us close to places unimaginably distant. It reveals beauty and violence, chaos and structure. And it does it without effort. Light doesn't need permission to travel, it just goes. The only requirement is time, but that time is the obstacle. Because no matter how fast light is, it's not instant. And in a universe this large, that means even the most basic communication across the stars is fundamentally delayed. If we sent a signal to a planet orbiting a star 100 light-years away, the message would take a century to arrive. And if someone responded immediately, their reply wouldn't reach us for another 100 years. A conversation that takes generations. A back and forth that spans lifetimes. This is part of what makes space travel, especially interstellar or intergalactic travel, so daunting. The distances aren't just far. They're set against a clock that doesn't bend. We might imagine faster-than-light travel in fiction, with warp drives and hyperspace lanes, but in reality, everything we send is bound to the speed of light or below. That means no real-time contact, no quick updates, just long, silent journeys. And it's not just human communication that's affected. Even light itself, for all its speed, can be outrun, not in absolute terms, but by the expansion of space. In some regions of the universe, galaxies are receding from us faster than light because of that expansion. That's allowed. It doesn't violate relativity because it's not motion through space. It's the growth of space itself. But the result is the same. Light from those galaxies will never reach us. It's already too late. The space between us is growing too fast for the light to bridge the gap. So light is a messenger, yes, but it's not an immortal one. There are parts of the universe it will never connect us to. Places we can never observe, no matter how long we wait, or how good our instruments become. And yet, within its reach, light gives us everything. It tells us what elements exist in a star by revealing their spectral fingerprints. It shows us motion through Doppler shifts, blue for approaching objects, red for receding ones. It maps gravitational lenses, the bending of light by massive objects, which lets us see things otherwise hidden behind galaxies or clouds of gas. Light even reveals things that don't emit light at all. Dark matter, for instance, doesn't glow. But we know it's there because of how it bends light around galaxies. We see the effects, the distortions, the fingerprints on the images we receive. That's indirect observation, but it's real. It's how we build knowledge in a universe where most of what exists can't be touched or visited. And that's what makes light so essential. It's not just useful, it's foundational. Without it, the universe would be invisible, not just dark, but unknowable. Every telescope, every satellite, every sensor we've built to study the cosmos depends on catching those faint beams of ancient light, some visible, some infrared, some ultraviolet, X-ray or gamma ray, each with its own message, its own story, its own path. Even now, new observatories are being launched, space telescopes tuned to frequencies our eyes can't detect. They'll peer deeper into space and farther into time, pulling in photons from the earlier stars, the first galaxies, the formation of black holes. They'll extend the reach of our cosmic conversation, adding new chapters to the oldest story we know. But no matter how good they become, they'll always be limited by time, because every photon that arrives today is a messenger from the past, a snapshot, not live feed. And every new photon we detect is part of a story still unfolding across distances we'll never cross. That's the trade-off. In a universe too large to travel across, light becomes our only traveller. It goes where we can't. It returns with news, and it does so at the maximum speed allowed, but never faster. So when we ask how we might cross the universe, we're really asking how we might go where light has already been, how we might move fast enough to catch up, or how we might use light not just to see the stars, but to understand what stands between us and them. And if light isn't fast enough for our needs, if its pace is too slow for crossing, then maybe we need to think differently. Maybe there's another way. A way not to chase the light, but to find a path around the slowness. Not through speed, but through a change in how space itself is shaped. If we're going to dream of travelling across the universe, or even across a tiny part of it, then at some point we have to confront the question of speed. Not just the idea of going somewhere, but going there fast enough to matter. Fast enough to reach another star within a human lifetime. Fast enough to leave our solar system and arrive somewhere meaningfully far away before everything we know has changed. At first glance, the solution seems obvious. Just go faster. If light can reach another galaxy in a few billion years, then all we have to do is get close to that speed. Build something powerful enough, efficient enough, advanced enough. Push harder, burn more fuel, and watch the stars get closer. But the universe doesn't work that way. Speed in space isn't like speed in a car or on a train. You can't just press the accelerator and expect the trip to shorten the way it does on Earth. Because here, we're not dealing with highways or tracks. We're dealing with fundamental limits. Not just practical barriers, but physical ones. The kind you can't push past, no matter how clever your design is. To understand why, we have to look at the rules that govern motion in the cosmos, particularly the ones shaped by Albert Einstein more than a century ago. His theory of special relativity wasn't just a refinement of Newton's mechanics. It was a redefinition of what motion is, what speed means, and how space and time respond when you try to move too fast. In everyday life, the effects of relativity are invisible. Drive down a highway at 100 kilometers per hour and nothing strange happens. Time doesn't slow, mass doesn't change, space doesn't bend. But the moment you start approaching the speed of light, even theoretically, everything begins to shift. According to relativity, as an object moves faster, its mass increases. Not in the usual sense of gaining weight, but in terms of how much energy is needed to keep accelerating it. The faster you go, the harder it is to keep speeding up, and the energy required doesn't increase linearly, it skyrockets. The closer you get to light speed, the more energy you need. And the equation doesn't level off. It goes all the way to infinity. That means no matter how powerful your engine is, no matter how perfect your fuel or futuristic your design, you can never actually reach the speed of light. You can get close, but each fraction closer costs exponentially more energy. And at some point the energy required becomes physically impossible. You'd need more than what the entire universe contains. It's not just impractical, it's forbidden by the laws of physics. So why not settle for a percentage? Say, 90% of light speed. That's still unimaginably fast. At that velocity, you could cross the distance between Earth and Alpha Centauri, our nearest stellar neighbour, in about 4.7 years from Earth perspective. That's a huge improvement over chemical rockets, which would take tens of thousands of years. And from the point of view of the traveller, time would actually pass more slowly. Thanks to time dilation, a crew on board such a ship might experience the trip as even shorter. Perhaps only a few months. The closer you get to light speed, the more time contracts for you. That's a real effect, confirmed by particle physics experiments and precision atomic clocks flown on high-speed aircraft. It's not just a theory. It happens, but there's a cost. Getting to that speed still requires enormous energy. The faster you go, the more energy is needed not just to accelerate, but to carry everything with you. The ship, the crew, the fuel. And the more fuel you need, the more mass you have, which increases the energy needed to move. It's a loop that gets worse the faster you go. This is known as the rocket equation problem. It describes how fuel requirements grow exponentially as you increase velocity, especially if you plan to carry your fuel with you. Every extra unit of speed demands more fuel, which adds more weight, which requires even more fuel to move. Eventually, the whole idea collapses under its own weight. To go faster, some proposals suggest collecting fuel along the way, scooping up hydrogen from the interstellar medium and fusing it in a high-efficiency engine. This is the basis for the Bussard ramjet, a concept proposed in the 1960s, but the density of usable material in interstellar space is incredibly low, just a few atoms per cubic centimetre, and the engineering required to make such a system work is still far beyond our current reach. Other ideas include using massive laser arrays based near Earth to push a lightweight spacecraft using light pressure, essentially beaming energy to a sail rather than carrying fuel on board. Projects like Breakthrough Starshot aim to use this principle to send tiny probes to nearby stars at a significant fraction of light speed. But these probes would be gram-sized, not ships, not habitats, just instruments with tiny cameras and transmitters sent as high-speed messengers. Even if such systems could work, they come with problems of their own: steering, power, communication, survival. A probe moving at 20% of light speed would cross enormous distances quickly, but even a speck of dust could destroy it. At those speeds, every particle in space becomes a deadly projectile. There's no shielding that can absorb that kind of impact without adding enormous mass, which defeats the purpose of keeping the craft small. Now, imagine scaling that up to a human-carrying ship, a vehicle capable of supporting life, shielding from radiation, protecting against micrometeoroids, and maintaining propulsion for years or decades. The energy requirements alone are staggering, and even if you manage to overcome those, there's still the issue of navigation. At relativistic speeds, your ship becomes effectively blind. Light from stars ahead becomes blue-shifted, compressed into higher frequencies, while stars behind redshift. The field of view contracts into a narrow cone in front of you. Reacting to obstacles or adjusting course in time becomes almost impossible. You'd need automated systems capable of detecting and responding to hazards at fractions of a second, faster than human reflexes allow. And all of this still assumes you don't want to stop at your destination, just arrive. Because decelerating from a high fraction of light speed isn't easy. It requires just as much energy as accelerating in the first place. If you don't plan for it, you arrive too fast to do anything except crash through a system and disappear into the darkness beyond. This is why fast travel in space isn't just an engineering challenge, it's a physics challenge. Not just building something strong, but confronting the fact that speed itself becomes a problem once you leave the familiar conditions of Earth. The universe doesn't offer easy shortcuts. It imposes limits that are deeply woven into the structure of space and time. Even going much slower presents problems. At just 1% of light speed, still 3,000 kilometers per second, it would take over 400 years to reach Alpha Centauri. That's still faster than anything we've ever built, but from a practical standpoint, it's almost unreachable. Our current fastest spacecraft, the Parker Solar Probe, reaches speeds around 200 kilometers per second. That's only 0.067% of light speed. To go even 1% would require orders of magnitude more energy and technology than we've ever developed. It's possible to imagine fusion drives, antimatter engines, or other exotic propulsion systems. These ideas live mostly in theory and simulation. Some are backed by serious physics, others stretch the imagination a little further, but none are ready, none are tested, and all of them face the same basic problem. The faster you try to go, the more the universe pushes back. There's also the human factor. At relativistic speeds, exposure to cosmic rays and interstellar radiation becomes more dangerous. Even today, astronauts in low Earth orbit receive higher radiation doses than people on Earth. In deep space, unshielded crews would face a constant barrage of high-energy particles, and at high speeds those particles hit even harder, like bullets. Protecting against them would require thick shielding, which adds mass, which demands more energy. And the loop begins again. The result is a kind of quiet wall. Not an absolute wall, not one that says travel is impossible, but one that says speed is costly, complicated, entangled in rules that don't bend just because we want them to. It's why even the most advanced space agencies in the world aren't designing crewed missions to other stars. The distances are too great, the energy requirements too high, the returns too slow. So if going fast is so hard, harder than it sounds, harder than it looks, then the real question becomes, is speed even the right goal? That's where some thinkers have turned their attention not to propulsion, but to geometry. Not moving through space faster, but altering space itself, compressing it, folding it, changing the path so that you don't need speed at all, just a different shape of the journey. And that's where concepts like wormholes and warp drives start to appear. Not because we can build them yet, or even know if they're physically real, but because they represent a way to think outside the speed limit, to get around the problem of going fast by asking whether we need to go at all. Because if space is flexible, if it can bend and stretch, then maybe there's a route through the universe that doesn't depend on acceleration at all, just a shift in the fabric itself. And maybe, just maybe, that shift is enough to change the entire question. If speed isn't the way forward, then what exactly is holding us back? We keep circling around one specific number, the speed of light, nearly 300,000 kilometers per second. The fastest thing we've ever measured, and the fastest anything can go, according to our best understanding of physics. That number isn't just a fact of nature, it's a boundary built into the structure of reality. One that Albert Einstein made central to how we understand motion, time, and space itself. Before Einstein, speed was more straightforward. If you were on a train going 50 kilometers per hour and you walked forward at 5 kilometers per hour, your total speed relative to the ground would be 55. The two velocities added together. That makes intuitive sense because that's how things work at everyday speeds. Newton's laws handle that kind of motion perfectly well. But as it turns out, that kind of math starts to break down when you get close to light speed. The breakthrough came in 1905 when Einstein introduced his theory of special relativity. One of the key insights was simple but strange. The speed of light is the same for all observers, no matter how fast they're moving. That goes against intuition. If you're standing still and shine a flashlight, the beam moves away from you at the speed of a light. If someone else is moving toward you at half the speed of light, you might expect they'd measure the beam approaching at 1.5 times the speed of light. But they don't. They still measure it as moving at the speed of light. Always the same. That consistency has consequences. To keep the speed of light constant, space and time have to stretch and compress depending on how you move. Time slows down for fast-moving observers, distances shorten in the direction of motion, and mass increases with speed. These aren't theoretical tricks. They're experimentally confirmed effects. They've been measured with atomic clocks on airplanes. They affect the operation of GPS satellites, which have to account for both time dilation from speed and from gravity. Relativity isn't an idea we've moved past. It's something we rely on every day without realizing it. But the most important consequence for our purposes is that no object with mass can reach the speed of light. The equations break if you try. As an object moves faster, its relativistic mass, the energy it carries with it, increases. The energy required to keep accelerating grows without bound. To reach the speed of light, you'd need infinite energy. And infinite energy is, by definition, impossible. That's Einstein's speed limit. It's not just a guideline, it's a hard stop. No signal, no object, no spaceship, no message can go faster. And that changes how we think about space travel. Because if you can't go faster than light, then the entire structure of distance and time across the universe is locked in place. No shortcuts through speed, no zipping across the stars. The limit isn't arbitrary. It's not like a speed limit on a road where you can technically break it if you're willing to risk a ticket. It's a boundary enforced by the geometry of space-time. The very fabric of reality is constructed in a way that makes this limit unavoidable. Light doesn't just move at the maximum speed. It defines the causal structure of the universe. What can affect what can reach what, and in what order. Think of it like this. Every event in the universe, a flash of light, an explosion, a decision, creates a bubble of influence, a zone that expands outward at the speed of light. Anything inside that bubble can, in principle, be affected by the event. Anything outside it cannot. That creates a kind of cosmic web of connections, where each point in space-time is linked only to the points that lie within its past and future light cones. Go outside those cones, and you're out of reach. Not just practically, but fundamentally. This structure has a name: causality. It's what keeps events ordered. Causes come before effects. Signals can't arrive before they're sent, and it's all enforced by the speed of light. If you could break that limit, if you could move faster, you could send messages backward in time, trigger effects before their causes, break the sequence of logic that underpins physics. This is why physicists treat the light barrier with such seriousness. It's not just about speed, it's about keeping the universe consistent, preventing paradoxes, preserving the arrow of time. So when we imagine travelling across the universe, we have to work within that structure. We can't just accelerate until we're going faster than light. We can't send messages instantly across galaxies. We're always bound by the light cone, always subject to the delay imposed by distance and the speed limit that defines it. But there's something else that makes this more complex. The speed of light is constant in a vacuum. That's important, because most of the universe is a vacuum, or very close to it. But light slows down slightly when it moves through materials, like water or glass. Not in a way that breaks relativity, because the ultimate limit still applies to information and energy in a vacuum. But it does mean light can be manipulated in interesting ways. Even more curious is the way certain quantum effects can make it look like something moves faster than light, without actually breaking the rules. In quantum tunneling, for example, particles can appear on the far side of a barrier instantly, as if they'd skipped over it without travelling the intervening space. But the math shows that no usable information or energy actually moves faster than light. The appearance of superluminal motion is an illusion, a quirk of probability waves and measurement. Then there's the phenomenon of entanglement, where two particles become linked in such a way that measuring one instantly determines the state of the other, no matter how far apart they are. Einstein famously called this spooky action at a distance, because it seemed to imply faster than light influence. But again, no information is actually transmitted that way. The outcomes are correlated, but not controllable. You can't use entanglement to send a message, so causality remains intact. All of this shows how tightly the speed limit is woven into the fabric of physics, not just as a barrier to travel, but as a guardrail that keeps the entire system coherent. Without it, the structure collapses, events lose their order, logic fails, and yet despite all this, we keep looking for ways around it. Not through brute force, but through cleverness, through geometry. If you can't go faster through space, maybe you can go a shorter path. Maybe you can change the shape of space itself so that the destination moves closer, without you having to accelerate at all. This is where the idea of space-time curvature becomes more than just a curiosity. In Einstein's general relativity, the extension of his work to include gravity, space and time aren't just passive backgrounds. They bend in response to mass and energy. Planets, stars, galaxies, all of them warp the fabric around them. That's what gravity is. Not a force in the Newtonian sense, but the result of objects following curved paths in a warped space-time. And if that's possible, then maybe it's possible to curve space-time in more extreme ways, to create shortcuts, folds, bridges. Structures that allow something to take a path through space that's effectively shorter than the one light would take, without ever moving faster than light locally. That's the dream behind concepts like wormholes and warp drives. They don't ignore Einstein's speed limit, they work within it, but they try to rewrite the map instead of racing across it. Of course, those ideas come with their own problems. Creating a wormhole requires exotic matter with negative energy density, something that might not exist in a usable form. A warp drive, like the Alcubierre concept, needs a bubble of space-time that compresses space in front of it and expands it behind. But again, the energy required is astronomical, more than what a star produces, and the stability of such a bubble is still in question. So while the speed limit remains, and while no one has broken it, the ideas it has inspired are anything but static. They've pushed us to think differently, to imagine forms of movement that aren't about speed at all. That's the strange legacy of Einstein's work. He didn't just tell us how fast we could go, he forced us to think about the nature of motion itself. And that thinking has led us back again and again to the structure of space, the shape of it, the possibility that distance isn't always fixed, that maybe somewhere in the fabric of the universe there are paths that light can't take, but that we might someday figure out how to follow. If the speed of light defines what can be reached, then it also defines what can't. And the more we understand that limit, the more we begin to realise there are parts of the universe we're fundamentally cut off from. Not because we lack the technology, or the ambition, or the time, but because the structure of space and time itself has placed them beyond our reach. That idea, that there's a boundary beyond which information cannot cross, leads us to one of the most quietly unsettling realities in cosmology, the concept of a cosmic horizon. We've already seen how light, even as the fastest traveller in the universe, takes time to reach us. That delay means we see distant objects as they were, not as they are. A galaxy 1 billion light years away is 1 billion years younger in our eyes. But as space continues to expand, some of those distant objects aren't just old, they're disappearing. Their light, stretched by expansion, grows fainter. Eventually it slows to a crawl, not because the light itself changes speed, but because the space between us grows so quickly that the light is red-shifted into oblivion. This expansion isn't like something being pushed outward from a centre. It's more like the stretching of the entire fabric of space everywhere at once. And as that fabric stretches, it doesn't just increase distance. It increases separation in a way that creates a moving limit, a horizon, a line beyond which light, no matter how fast or how long it travels, will never reach us. There are a few different kinds of horizons in cosmology, but one of the most important is the particle horizon, the maximum distance from which light has had time to reach us since the beginning of the universe. That's what defines the observable universe. Everything inside that sphere, about 46.5 billion light-years in every direction, is where photons have had time to complete the journey. Everything outside that, still silent, still unseen. That's the past boundary, a measure of what can be observed. But there's another horizon that's perhaps even more profound. The event horizon of the universe, not the same as a black hole's event horizon, but similar in meaning. It's the limit beyond which light sent toward us today will never arrive, no matter how long we wait. Not because of dust, or darkness, or distance, but because the space between is growing faster than the light can cover it. This isn't a fixed line. It depends on the rate of expansion, which itself depends on the amount and behaviour of dark energy. Observations over the past few decades suggest that the expansion of the universe is accelerating. That means more and more of the universe is drifting beyond our reach, not in space, but in time. The light from those galaxies is still moving, still heading toward us, but the finish line is receding faster than the light can gain ground. Eventually, galaxies we can see now will fade away. One by one, they'll fall over the horizon. Not with a flash or a sound, but with a gradual dimming. Their light will stretch into longer wavelengths, then into microwave, then radio, and finally into nothing. That process takes billions of years, but it's happening. The future universe will be darker, not because things are dying, but because the distance between everything is growing too fast for visibility to keep up. That's the concept of a cosmic event horizon. A limit, not in space, but in observability, and it has consequences, because anything beyond that line is permanently unreachable, not just for us now, but for anyone, ever. That light is lost to us, and if travel is bound by the same rules, then so is motion. There are places we can never go, not because of practical limitations, but because the structure of the universe has made them unreachable. It's not easy to grasp what that means. We tend to think of space as being open, at least in theory. Give it enough time, enough fuel, enough technology, and you can go anywhere. But the horizon tells us that's not true. There are parts of the universe we'll never visit, never see, never know. Not because they're too far, but because they've moved past the boundary of connection. The light they send today will never arrive, and if we sent a ship in their direction, it wouldn't reach them either. The destination would keep moving away faster than the ship could travel, like trying to catch the edge of a shadow that retreats as you move toward it. This brings us to a deeper question. If the universe has a horizon, does that mean it has an edge? The answer, strangely, is no. The universe doesn't have an edge in the traditional sense. It may be infinite, or it may be curved back on itself in ways we don't yet fully understand. But the horizon isn't a physical border. It's a consequence of time and motion, of what's been able to reach us since the beginning and what still has the potential to do so. Imagine standing in the middle of a vast foggy plain. You can see a certain distance in every direction, limited by how far sound or light can travel. Beyond that, the plain continues. There's no wall, no cliff, no drop, just more of the same, hidden by the fog. That's what the cosmic horizon is like. It doesn't mark the end of the universe, just the end of what's accessible. Now we might wonder, is the horizon the same for everyone? Or does each observer have their own? The answer is, once again, a little stranger than expected. The horizon is relative. Every observer in the universe, no matter where they are, sees themselves at the centre of their own observable sphere. That doesn't mean anyone is in a privileged position. It just means that the light reaching you has travelled through your specific path in space-time. A galaxy 10 billion light-years away sees its own observable universe centred on itself. Some of what it sees overlaps with what we see, some of it doesn't. From its point of view, we're also 10 billion light-years away. It sees our past, just as we see its past. And just as we have a horizon, so does it. The structure repeats everywhere, not because the universe has a centre, but because every point experiences its own version of time and light. This also means that as time passes, our horizon grows. Light from more distant regions has time to arrive. The observable universe gets bigger, but only slowly, and the accelerating expansion means that, at some point, even though the past horizon grows, the event horizon, the future limit, shrinks. There's a shrinking window for new light to reach us. Eventually, most of the universe will be out of contact permanently. That's a hard concept to sit with. The idea that the majority of the universe will vanish from view, not because we turned away, but because it crossed a line we didn't draw. A moving line that separates what can still reach us from what never will. And it's not just distant galaxies. In the far future, trillions of years from now, even the nearest galaxies will move beyond the horizon. All that will remain visible are the galaxies gravitationally bound to ours. The local group, a small cluster of galaxies including the Milky Way and Andromeda, will merge into a single massive galaxy over time. Everything else will disappear. The sky will grow emptier. New observers born in that future era will see a very different universe. One without visible evidence of cosmic expansion. One where the observable universe appears quiet, small, and isolated. That's the long-term view. But even now, We see hints of the horizon in the way light behaves, the redshift of distant galaxies, the faintness of ancient quasars, the thinning out of detectable signals from the cosmic background. All of it points to a universe in motion, not just motion through space, but motion of space itself. And that raises another question. If some galaxies are beyond the horizon, does that mean they no longer exist? The answer depends on what we mean by exist. They did exist when they emitted the light we see. They may still exist now, continuing their lives, forming stars, rotating, colliding. But we can't confirm that. Their present, if they have one, is beyond our knowledge. We can only see the image they left behind, and that's not a flaw in our instruments. It's not something better technology will fix. It's a limitation set by the universe itself. The structure of causality, the light cone, the rules of motion. So when we ask if we can travel across the universe, the horizon forces us to clarify what that really means. Are we talking about going from one side of the observable universe to the other? Or are we imagining a trip beyond the horizon, to a part of space that no light will ever reach? Because if it's the latter, then we're dealing with more than engineering challenges. We're dealing with a fundamental separation, a cut in the fabric of connectivity, a place that is not just far but unreachable, not temporarily but forever. And if that's true, then our universe is larger than we can ever explore, not just practically but physically. Entire regions are out of contact, entire galaxies, perhaps infinitely many, are moving away from us not slowly but permanently. It doesn't mean those places aren't real. It just means they're disconnected, not part of our story anymore, and we, in turn, are disappearing from theirs. In a sense, every galaxy is an island, slowly becoming more alone as the sea of space expands. And so we come back, again, to the question of connection. If speed won't get us there, and if expansion makes the destination unreachable, then perhaps the real challenge is finding some other way to reconnect what's been pulled apart. Maybe, somewhere in the theory, there's a loophole, a tunnel, a fold, a way not to chase the retreating edge but to leap ahead of it. If the universe is pulling itself apart faster than we can chase it, and if the speed of light sets a ceiling we can't crack, then the most tempting idea left is one that turns the whole game on its side. Instead of pushing ourselves faster and faster across the growing void, maybe we don't have to cross it at all. Maybe we could reshape space itself, shrink the distance rather than trying to cover it. That shift in thinking is what leads to one of the most fascinating and often misunderstood ideas in physics, the possibility of bending space. It starts with a change of perspective. In everyday life, we treat space as a background, static, reliable, a flat surface we move across. You walk across a room, or fly across a continent, and you don't need to think about space itself changing. It's the canvas, not the paint. But when Einstein introduced general relativity, that entire framework changed. Space wasn't just a stage anymore, it became part of the performance. According to general relativity, space is dynamic. It can curve, stretch, warp, and ripple. Not metaphorically, but physically. Massive objects, like planets and stars, don't just exist in space. They alter it. They bend it. Gravity isn't a force in the old Newtonian sense. It's the result of objects following the natural path through curved space-time. This is more than just a visualization trick. It's measurable. The bending of starlight near the sun during a solar eclipse was one of the first confirmations of Einstein's theory. It's also how gravitational lensing works. Distant galaxies and quasars appear distorted or duplicated when their light passes through a massive cluster on its way to us. That lensing isn't caused by glass or air, it's caused by the curvature of space. If mass can bend space, then the natural next question is, can we bend space intentionally? Not with stars and planets, but with technology, or with carefully shaped fields. Could we take advantage of space-time's flexibility and mould it into a shape that shortens the path between 2 points? In principle, the answer is yes. Space-time is malleable, at least under the right conditions, but the devil is in the details, or more precisely in the energy. One idea that has captivated scientists and science fiction writers alike is the concept of a wormhole, a shortcut through space. Not a tunnel in the usual sense, but a kind of bridge that connects two distant regions of space-time. If such a structure exists, it could, in theory, allow something to move from one point in space to another without crossing the intervening distance. The path through the wormhole would be shorter than the path through normal space, not by changing the traveller's speed, but by changing the geometry itself. Wormholes aren't just fantasies. They appear as valid solutions in Einstein's equations under very specific conditions. The math allows for them. But allowing something on paper and building it in reality are two different things. The kind of wormhole that would be useful, one that stays open, remains stable, and is large enough for something to pass through, would require a very peculiar ingredient: negative energy. Not just low energy, or zero energy, but energy with negative density. This is not something we encounter in daily life, and while quantum physics suggests that negative energy can exist in tiny amounts over short timescales, through phenomena like the Casimir effect, we don't know how to produce or sustain it on the scale needed to support a macroscopic wormhole. Without that exotic matter, a wormhole would collapse before anything could pass through. The tunnel would pinch shut instantly, or worse, it would collapse into a black hole, swallowing anything near it. That makes the whole concept extremely speculative. Not impossible, but highly theoretical. Then there's the question of whether wormholes, if they existed, would actually allow for faster-than-light travel. From the traveller's point of view, you'd never exceed light speed locally. You'd simply take a shorter route. But from the outside, it could appear that you've travelled faster than light, arriving at a destination sooner than any signal could have travelled through normal space. That leads to complications with causality. If you can arrive somewhere before light could, then under the right circumstances, you might be able to set up scenarios where events loop backward in time. The math allows for such possibilities, closed time-like curves, but whether they're physically meaningful or just mathematical artifacts is still an open question. Another approach to bending space comes from the idea of a warp drive, not the kind from science fiction with glowing engines and techno-babble, but a specific concept first proposed in the 1990s by physicist Miguel Alcubierre. The Alcubierre drive imagines a bubble of space-time that contracts space in front of it and expands space behind. Inside the bubble, a ship could sit still, not moving through space at all, while the bubble itself carries it forward. Since nothing inside the bubble moves faster than light, the rules of relativity aren't violated locally. But the distance between start and destination could be covered more quickly than light could manage through flat space. It's a clever idea, a way to get around the speed limit without breaking it. But it comes with massive caveats. First, like wormholes, the Alcubierre drive requires negative energy, and lots of it. The original formulation demanded more energy than exists in the observable universe. Later refinements reduced that requirement, but we still don't know if such negative energy can be produced in meaningful amounts. Second, there are serious questions about stability. Would the bubble collapse? Could it be controlled? What happens to the space at the boundary? Some analyses suggest that the warp bubble could gather up radiation or particles as it moves, releasing them all at once when it stops, potentially with catastrophic consequences. Others point out that signals can't escape the bubble from inside, which raises questions about how you'd steer or stop it. Then there's the question of whether creating such a structure is even possible. The math allows it, but we've never observed anything like it in nature. It remains purely theoretical, a playground for equations, but not yet for engineering. Still, the very fact that these ideas are taken seriously by physicists, studied, refined, debated, tells us something important. Space isn't fixed, it's dynamic, and in principle, it can be shaped. That opens the door to new kinds of thinking. Maybe, instead of accelerating through space, the next great leap involves manipulating space itself. Not propulsion, but geometry. Not engines, but fields. The tools for that are far beyond what we have now. Creating even the smallest space-time curvature requires massive amounts of mass or energy. Our most powerful machines, particle accelerators, nuclear reactors, entire planetary engines if they existed, still wouldn't come close to what's needed. But ideas have a way of outlasting limitations, and the math of general relativity continues to hint that space is more flexible than it appears. If we ever learn how to manipulate that flexibility directly, not through massive objects but through engineered fields or new forms of matter, then travel across vast distances might stop being about speed altogether. It's worth noting that even now, we manipulate space on small scales without realizing it. Our satellites rely on relativistic corrections because the Earth's gravity bends space-time. The global positioning system wouldn't work if we didn't account for that. In that sense, we're already adjusting for space-time curvature, not creating it, but responding to it. The question is whether that can go from passive to active, from compensation to control, from observing curvature to generating it. Until then, the possibility of bending space remains one of the most intriguing what-ifs in modern physics. Not because we're ready to build warp drives or open wormholes, but because these ideas show us how incomplete our assumptions are. We're used to thinking of distance as something absolute, a number, a measurement. But if the fabric of space can be reshaped, then distance is negotiable. Travel becomes a question of geometry, not speed. And the road to the stars may not be a road at all, but a fold, a crease, a rearrangement. That brings us to a deeper problem, not one of space, but of time. Because even if you could bend space to shorten the journey, you'd still have to deal with the way time behaves near massive distortions. That's the next part of the puzzle. What happens to time when space is no longer flat? When it curves, folds, or collapses? What does travel mean when your clock ticks differently from everyone else's? The more we learn about space, the clearer it becomes that distance isn't always what it seems. And if the shape of space can change, then maybe there's a way to use that flexibility to do something even more dramatic than shrinking a journey. Maybe instead of crossing space, or even bending it, we could bypass it completely by stepping through a bridge that connects two separate locations. That's the idea behind a wormhole. The name sounds simple, even playful. It comes from an old analogy. Imagine a worm crawling across the surface of an apple. The long way around, from one side to the other, is the obvious route. But if the worm could burrow straight through the fruit, it would take a much shorter path. In that sense, the tunnel, the wormhole, is a shortcut through a three-dimensional space that connects 2 points more efficiently than the surface allows. Now replace the apple with the entire universe. A wormhole, in theory, would be a kind of tunnel through higher dimensional space, connecting two locations in our universe, or perhaps even two different universes if such things exist. The entry and exit points could be extremely far apart in conventional terms, separated by light years or more, but linked through a shortcut that's much shorter than the space between them. The idea isn't purely fictional. Wormholes show up as valid solutions in Einstein's equations of general relativity. The first known solution was discovered in 1916, just after Einstein published his theory, but it wasn't recognised as a wormhole at the time. Later, in 1935, Einstein and his colleague Nathan Rosen explored a concept now called the Einstein-Rosen bridge, a connection between two black holes. They were looking for ways to avoid the idea of singularities, the infinitely dense points at the centre of black holes. What they found was a mathematical structure that in theory linked two separate regions of space-time, but there was a catch, or several. Most versions of these bridges are unstable. They pinch off too quickly to allow anything to pass through, or they collapse under the influence of their own gravity. or they become singularities themselves, impassable and destructive. That's why most wormholes are treated as mathematical curiosities rather than real objects. Still, the idea wouldn't go away. In the 1980s, physicists like Kip Thorne began exploring whether there might be a way to keep a wormhole open. What they found was that it might be possible, but only if you had access to something very strange: negative energy. Negative energy isn't just the absence of energy. It's a kind of energy that does the opposite of what we expect. Instead of pulling things together, it pushes them apart. Instead of curving space inward, it curves it outward. That's the kind of effect you'd need to hold a wormhole open, to keep the tunnel from collapsing under its own gravity. In theory, quantum physics does allow for negative energy, at least in very small amounts, over very short times. One example comes from the Casimir effect, where two metal plates placed very close together in a vacuum experience a tiny attractive force, caused by differences in quantum fluctuations on either side. That's a real, measurable phenomenon. It suggests that the vacuum of space isn't truly empty. It's full of energy, some of it negative. But creating and controlling negative energy in amounts large enough to stabilise a wormhole is another matter entirely. We don't know how to do it. We don't even know if it's physically possible on macroscopic scales. The math says it's required. Reality hasn't confirmed that it's available. Assuming, for the sake of exploration, that we could somehow access this exotic matter, a traversable wormhole would still come with conditions. For one, the entry and exit points, called mouths, would need to be held apart. That's not a small thing. If you place them near each other, they could collapse into a single massive object, behaving more like a black hole than a bridge. You'd need some way to stabilise the geometry, to keep the tunnel from distorting or folding in on itself. Then there's the question of where the mouths are located. In principle, they could be placed anywhere, in space or in time. That's one of the strangest implications of wormholes. If you move one mouth relative to the other, time dilation could turn the bridge into a kind of time machine. That's not science fiction logic. It's a real consequence of relativistic physics. Imagine holding one end of a wormhole stationary, while moving the other end at near light speed for a while, then bringing it back. The moving end would experience less time than the stationary one due to time dilation. If the wormhole remains open and stable, then entering one mouth could mean exiting the other at an earlier or later time. That creates the possibility of closed time-like curves, loops through space-time where an event could influence its own past. This raises all the usual paradoxes associated with time travel. Could you go back and prevent yourself from entering the wormhole in the first place? Would events become inconsistent? Or would the universe prevent such contradictions through some unknown mechanism? Physicists don't have a consensus answer. Some argue that wormholes leading to the past are forbidden by principles like the chronology protection conjecture, which suggest that the laws of physics conspire to prevent time travel. Others believe that quantum effects would destroy such wormholes before they could be used. Still others think that causality might be preserved through self-consistent loops, where events influence the past, but only in ways that maintain consistency. The point is, wormholes are not just shortcuts through space, they're shortcuts through space-time, and that means they touch every part of the structure we usually take for granted: distance, motion, order, cause and effect. Even if a stable wormhole could exist, it wouldn't necessarily be a universal solution. The mouths would have to be created and placed beforehand. You couldn't simply generate a wormhole to anywhere you wanted to go. You'd need to build it in advance, or find one already existing. That raises another possibility. What if wormholes already exist in nature? Could they form naturally, like black holes or neutron stars? Some theories suggest they could, particularly in the early universe, when densities and energies were extreme. But if they did form, and if any survived, we've never observed one. No gravitational lensing that suggests a tunnel, no strange signals that can't be explained by other means. Detecting a wormhole would be extremely difficult. It might look like a black hole, distorting light, bending space, but without the deadly singularity. Or it might be completely invisible unless something passed through it. There have been searches for such anomalies, especially with sensitive astronomical surveys, but nothing has been confirmed. That doesn't mean wormholes don't exist. It just means for now they're still theoretical. That's not a failure. It's part of the process. We build ideas from equations and possibilities long before we build them from metal and energy. And wormholes remain one of the most intriguing structures allowed by the mathematics of general relativity. Even if we never find one, studying them teaches us about the limits of motion, the structure of time, and the possibilities that exist when we stop assuming space is flat and fixed. It challenges us to think beyond linear paths, beyond going faster. It forces us to consider what it would mean to step sideways in the fabric of the cosmos, not moving through space but around it. The conditions are steep, the requirements are exotic, the risks are enormous. But the concept remains one of the few ideas that even begins to answer the question, is there a way to travel without crossing, to arrive without enduring the journey, to go not faster but smarter? And just as importantly, wormholes point toward a much broader shift in thinking. That maybe motion isn't the only kind of travel, that maybe space isn't the obstacle, it's the material to be shaped. If wormholes suggest the possibility of jumping from place to place through a shortcut, warp drives offer something different. Not a jump, but a glide. Not through space, but with space. Instead of trying to bypass the terrain, they propose to move it. The ship doesn't travel faster than light. Space itself does the moving. The idea has a simple surface appeal. Instead of pushing a ship to ever higher speeds, limited by mass and energy and relativity, you take the medium it's sitting in and reshape it. Compress the space in front of the ship. Expand the space behind it. Let the ship sit in the middle, motionless relative to its local space, while space itself carries it forward. That's the essence of a warp drive. In that picture, the ship never violates the speed of light locally. Everything inside the warp bubble follows normal rules. No atoms are breaking laws, no particles are exceeding limits. But to an external observer, the ship seems to move faster than light would through flat space. The trick is that nothing inside the bubble has to break the rules, because the rules don't apply in quite the same way when space itself is changing. The most well-known theoretical model for this is the Alcubierre drive, proposed by Mexican physicist Miguel Alcubierre in 1994. Using Einstein's field equations, he showed that a specific configuration of space-time curvature could allow for effective faster-than-light motion without violating the local laws of physics. His model describes a bubble of flat space-time surrounded by a shell of space-time curvature, negative energy in the front to contract space, and positive energy in the rear to expand it. That bubble would carry whatever's inside it, and in theory, it could move faster than light through external space, simply because the space around it is doing the stretching and contracting. The ship inside the bubble isn't accelerating at all. It just rides the wave. But as elegant as the concept is, it's not without serious issues. The first and most immediate is the matter of energy. When Alcubierre first proposed the idea, the energy required to create even a small warp bubble was astronomical. Some estimates put it at more than the mass energy of the entire observable universe. Later refinements, using different geometries or assumptions, brought that requirement down, but only slightly. Even optimistic versions still require more energy than anything humanity could produce. And worse, it's not just any kind of energy. It requires negative energy, or more precisely, a region of space-time with negative energy density. Just like the traversable wormhole, the warp drive depends on exotic matter, stuff that behaves in ways no known substance does. While quantum theory allows for brief, small negative energy states, there's no evidence they can be sustained or scaled up. Assuming somehow that exotic matter could be created or managed, the next problem is control. A warp bubble moves space itself. That means normal engines or steering systems wouldn't work. You can't apply thrust to control a bubble of space-time. You'd need some kind of field manipulation to generate and direct the curvature. That implies a whole new kind of technology, something that can shape space-time like clay. And then there's the question of entry and exit. Once you're inside the bubble, how do you get out? Some versions of the theory suggest that nothing inside the bubble can communicate with the edge. Information, signals, commands, all trapped. That makes stopping or changing direction problematic. You could find yourself unable to steer, unable to decelerate, carried forward until the bubble collapses, or hits something. There's also the issue of what happens at the front edge of the bubble. As the bubble moves through space, it gathers up particles and radiation. These accumulate at the front, compressed and energized. When the bubble stops, all that stored energy is released at once. The result, according to some models, could be catastrophic. A blast of high-energy radiation equivalent to a small supernova. Not an ideal arrival. Other concerns include the effects on space-time itself. A warp bubble that distorts space on large scales could create gravitational waves or other unpredictable side effects. It could tear or stretch space-time in dangerous ways, especially if something goes wrong with the field structure, and if the drive creates closed time-like curves, as some variants might. It could raise paradoxes of causality, potentially leading to logical inconsistencies or instabilities. Despite these concerns, research into warp drives hasn't stopped. It's remained mostly theoretical, but a few labs and institutions have explored the idea at a conceptual level. NASA's EagleWorks laboratory, for instance, examined low-energy configurations that might produce detectable space-time distortions, not for full warp travel, but to test the underlying principles. Other researchers have published revised models that reduce energy requirements or adjust assumptions about the geometry of the bubble. But so far, no experiment has detected a warp field. No prototype has shown even the faintest sign of bending space. The equations remain interesting, but the engineering remains out of reach. Even so, the Alcubierre drive has captured imaginations, and not just because it's exotic. It offers a glimpse of what space travel could be if we moved beyond traditional propulsion. If space can be reshaped, then motion doesn't have to come from engines or exhaust. It can come from geometry, from manipulating the medium itself. That's a powerful idea. Because in a universe where distances are measured in light years and horizons move faster than we can catch them, conventional motion may never be enough. Rockets can only go so fast, fuel can only burn so long. But space, if it's flexible, if it can be pushed and pulled, could open entirely new pathways. Some researchers have looked for analogues in nature. Are there any known phenomena that resemble a warp bubble? So far, the answer is no, not on large scales. But there are hints, in the mathematics, that space-time is more responsive than we tend to think. Quantum field theory, for instance, describes a vacuum that isn't empty, a sea of fluctuating energy that interacts with particles and fields. If that vacuum can be influenced, maybe it can be shaped. Theoretical models like quantum gravity or string theory go even further, describing space-time not as a smooth continuum, but as a granular or vibrational structure, something with deeper properties, not yet fully understood. If those properties can be tapped into, the door to manipulation might open a crack. Even if warp drives as originally imagined turn out to be impossible, the broader principle, that we might travel by reshaping the terrain could survive. Maybe there's a way to create local gradients in space-time that allow for new forms of propulsion. Maybe the future of space travel doesn't look like a ship racing through a vacuum, but like a platform sliding along a ripple. Maybe the key is not to move through space, but to move space through us. In any case, the warp drive remains one of the few ideas in physics that seriously addresses the question of long distance, rapid travel, without violating fundamental laws. It doesn't ask us to go faster than light. It asks us to rethink what it means to move at all, and that rethinking continues to ripple through physics, It raises questions about what's possible in the presence of strong gravitational fields, about the interaction between space-time and energy, and about whether space is a passive arena or an active participant. If nothing else, warp drives remind us that space isn't flat, it isn't fixed, it isn't empty, it's something that can be shaped, at least in theory, and that shaping could offer ways to cross impossible distances, not by going faster, but by changing what distance even means. Every time we talk about distance in the universe, whether through space or across theoretical bridges, there's something else woven into the story just beneath the surface. It's always there, moving alongside us, ticking at its own pace. Time. We treat it as a backdrop, as if it's always the same no matter where you are. But the moment we begin to travel far or fast, especially through the deep fabric of space, time starts to act differently. The truth is, time and space aren't separate. They're part of the same structure, space-time, and anything that changes how we move through space also changes how we experience time. So the further we go, the faster we try to move, the more space we distort or bend, the more time starts to shift in ways that aren't always obvious. To begin unravelling this, we go back again to Einstein. Special relativity tells us that the faster you move, the slower time passes for you, relative to someone who's standing still. It's not a metaphor or a theory awaiting proof. It's been tested, observed and measured. Time dilation is real. Clocks flown on planes tick ever so slightly slower than clocks left on the ground. Muons, particles created in Earth's upper atmosphere that should decay in microseconds, survive long enough to reach the surface when they travel close to the speed of light. Their internal clocks slow down from our perspective, giving them extra life. These effects are small at low speeds, but they grow dramatically as you approach light speed. Now imagine a spacecraft travelling to a distant star at 90% the speed of light. To observers on Earth, the trip might take years, but to the people on board, the journey could feel much shorter. Maybe months, maybe weeks, depending on the speed. That's because their time is unfolding more slowly from our point of view. Their experience compresses. They age less. This raises strange questions. What does it mean to go somewhere if the time it takes depends on who's watching? If two people leave from the same point, take different paths and return with different ages, which one experienced real time? The answer is, they both did. Time isn't universal, it's personal. It depends on your path through space-time. Two different paths can lead to two different experiences of time. That's not science fiction. That's how the universe works. Now bring in general relativity, and things get even more complex. Gravity also affects time. The stronger the gravitational field, the slower time moves. Again, this isn't theory. It's measured and accounted for in the GPS satellites that orbit Earth. If they didn't correct for gravitational time dilation, their location data would drift by kilometers per day. Time moves faster for them, higher above Earth's gravity well than it does for people on the surface. So if you travel near a massive object, a neutron star, a black hole, your time slows down. Stay close enough, and seconds for you could be years for someone far away. That's not just poetic exaggeration, it's mathematical fact. Black holes don't just trap light, they trap time. The closer you get to the event horizon, the more time slows relative to distant observers. From the outside, it looks like you freeze. From your point of view, time continues as normal, but the rest of the universe accelerates wildly. Now put all these ideas together. Velocity, gravity, distance, and curvature. If you want to travel across the galaxy using any method, rockets, wormholes, warp drives, you're not just navigating space. You're reshaping your experience of time. You're deciding how much you'll age compared to the rest of humanity. You're choosing a path that may place you far ahead or far behind in the unfolding of history. For example, let's say you build a ship capable of travelling at 99.9% the speed of light. You leave Earth, travel for what feels like 5 years to you, then return. On your ship, you've aged 5 years. But Earth has aged much more, maybe 50 years, depending on how fast and how long you've gone. That means interstellar travel, even if possible, would come at a cost. You might reach your destination, but everyone you knew would be gone or changed. Your origin would be in the past. You'd become a kind of time traveller, not through machines or paradoxes, but simply by moving quickly. That might sound like a solution to long-distance travel. Just move fast enough and let time slow down for you. But it doesn't help with communication. You can't take the rest of civilization with you. Your messages are still limited by light speed. You might arrive at your destination quickly, from your perspective, but Earth will still be far behind in both space and time. Even the most exotic ideas, like wormholes and warp bubbles, to have time complications. Wormholes especially can create mismatches in time between their two mouths. If one end experiences time differently from the other, they can fall out of sync. Travel through the wormhole could send you not just across space, but into another era. Whether that's forward or backward depends on how the mouths have moved relative to each other. This isn't just a hypothetical problem, it's built into the math, and it raises serious questions about what's allowed. Could time travel into the past actually occur? Some physicists think the universe has built-in protections against that. Feedback loops or quantum instabilities that destroy wormholes before they can be used that way. Others believe consistent time loops could exist, but only if they avoid contradictions. And some leave the door open, cautiously, saying the laws aren't yet fully understood. Warp drives, too, may have time consequences. The stretching of space, the movement of the bubble. These may alter the traveller's relation to time outside the bubble. Depending on how it's constructed, a warp field could move a ship far into the future, even if only a short time passes inside. The ship might seem to move faster than light, but at the cost of disconnecting from the timeline it started in. This is where relativity becomes more than physics. It becomes a psychological challenge. Because once you start changing your relationship with time, you're changing your connection to people, to memory, to meaning. You're not just going somewhere, you're leaving behind when you came from. And time, as much as we think we understand it, resists being held still. It unfolds for each of us, tied to motion and gravity, to experience and measurement. It's not a universal rhythm, it's a landscape, a terrain shaped by speed and mass and movement. We each carve our own path through it, whether we stay at home or travel to another star. Even now, astronauts on the International Space Station experience time slightly differently than we do on Earth. Their clocks tick a bit slower due to velocity, a bit faster due to weaker gravity. The result is small, microseconds, but measurable. Over long durations and higher speeds, those differences grow. Over interstellar scales, they become central. So when we talk about reaching another galaxy, we have to ask, what kind of time are we hoping to preserve? Do we want to arrive somewhere else and find a familiar present waiting? Or are we willing to accept that arriving quickly may mean losing the present we left behind? Maybe someday, someone will step onto a ship, travel at a fraction below light speed, and reach a star system dozens of light years away. For them, it may feel like months, but for Earth, it will be generations. Letters won't arrive, news will be old before it gets there. And returning would mean coming back to a future they never lived through. That future may be unrecognisable, or it may be silent. The journey would be fast, but the cost would be time. Not the traveller's time, but everyone else's. And then there's the question of perception. If you're moving at a high speed, the outside universe appears different. Light becomes blue shifted in the direction you're moving, red shifted behind you. The sky contracts into a cone in front of you. Even the way stars appear changes. Your visual and sensory world bends around the path you're taking. Space travel, then, isn't just about where you go. It's about how you experience the going. It's about what you're willing to lose in time to gain in distance. And it's about what kind of timeline you want to belong to when you arrive. Even bending space, even folding it or slipping through shortcuts, doesn't erase the consequences. The further you go, the more time separates you from your origin. And sometimes, the cost of arriving isn't distance, it's irreversibility. You can't go back and find things the way they were. You've moved not just through space, but through a clock that doesn't run backward. So when we imagine crossing the universe, or even just touching another star, we aren't only imagining speed or distance, we're imagining time, not just what it takes, but what it does to us, what it changes, what it leaves behind. And that's where the next question begins. Not about motion, or even possibility, but about purpose. Why do we want to travel across the universe? What are we looking for? And what do we hope to find on the other side of time? Time always moves forward, but not always at the same speed. That becomes clear the moment we step outside the slow rhythms of everyday life and into the realm of high velocities and cosmic distances. We've already seen how speed and gravity can stretch or compress time depending on your path through space. But there's a classic thought experiment that brings this into sharper focus. A scenario that's been discussed for decades, not because it's unrealistic, but because it makes the reality of time dilation unmistakable. It's called the twin paradox. The setup is simple enough. Imagine two identical twins. One stays on Earth, living a normal life. The other boards a spaceship capable of travelling at speeds close to the speed of light. The travelling twin accelerates away from Earth, cruises through space for a while, then turns around and returns. The journey feels brief to the one on the ship, maybe a few years, but when they step off the spacecraft and reunite with their sibling, they discover something strange. Their twin is much older, maybe decades older. In some versions of the scenario, the Earthbound twin has grown old, or even passed away, while the traveller has only aged a few years. At first, this seems like a contradiction. From the traveller's perspective, wasn't the Earth the thing that was moving? Shouldn't the roles be symmetrical? Shouldn't the twin on Earth also have experienced slower time? But relativity isn't about symmetry alone. It's about frames of reference, and more importantly about changes in motion. The key to the paradox lies in the fact that the travelling twin turns around. They accelerate, decelerate, and switch directions. That change in velocity breaks the symmetry. One twin stayed in a single inertial frame, the other didn't. That shift makes all the difference. It's not just about moving fast, it's about changing how you move. That's what determines who ages more. And while this may sound like a purely academic example, the math behind it has been tested with real particles and precise clocks. It holds up, it works, and it paints a very strange picture of what time is like when you go far enough, fast enough. This isn't just an intellectual exercise, it has implications for how we think about travel, communication, and even identity. Because the moment you accept that time can move differently for different people, you also accept that the future isn't the same for everyone, that you can, in a sense, move into tomorrow, not metaphorically, but literally. Let's say you built a ship that could maintain high speeds for extended periods, 99.99% the speed of light. If you travelled at that speed for what felt like 5 years to you, you could arrive back on Earth to find that centuries had passed. The people you knew, the culture you left behind, the technologies and histories, all of it would be part of a future you skipped over. You'd be younger than your own descendants. You'd step into a world that to you had leapt forward in time. And again, this wouldn't be a trick or an illusion. It would be how time actually passed for you, based on the physics of your journey. You'd have travelled into the future, not by crossing timelines, but by choosing a path through space-time that caused your internal clock to tick more slowly than the world's. This raises another question. Can we ever travel into the past? Relativity doesn't rule it out completely, but it makes it very, very difficult. The kinds of structures that might allow backward time travel, like certain wormholes or theoretical constructs like rotating universes, require physics that's speculative at best and impossible at worst. So far, no evidence suggests that backward time travel is possible, or that causality, the order of cause and effect, can be violated. But forward time travel, that's real. It's measurable. It's already happening in small ways on satellites, space stations, and aircraft. The scale is small, microseconds here and there, but it grows with speed and gravity. The twin paradox isn't science fiction, it's just a matter of scale. For practical space travel, this has strange consequences. The longer you travel at high speeds, the more you separate yourself from the timeline you left behind. You don't just travel across light years, you skip ahead in history. That might be useful in some sense. It means we could reach distant worlds in a single lifetime, at least from the traveller's point of view. But it also means leaving behind the present, permanently. Imagine being part of a mission to another star. You train, you launch, and you spend what feels like a few years in transit. When you arrive, the Earth you knew is gone. 1,000 years have passed. New languages, new governments, new ideas, a civilization you've never seen. You haven't aged much, but the world has moved on without you. You've skipped forward in a way no one on Earth could follow. This could be one reason why we haven't met other civilizations. If intelligent species take to the stars and travel at relativistic speeds, they may all be slipping forward in time, arriving at planets long after their own civilizations have changed or disappeared. The silence of the cosmos may not be due to absence, but to desynchronization. Everyone is out of phase, and yet there's something hauntingly beautiful about this idea. That time, like space, can be explored. That we're not trapped in a single stream, but that our trajectory through the universe can affect not just where we go, but when we arrive. This makes every journey a choice, not just about destination, but about era. Do you want to go far and fast, knowing you'll leave your time behind? Or stay close and present, accepting that the stars will remain distant, but your place in history stays anchored? Is a trade-off, one we don't yet have to make, but one we'll face if interstellar travel becomes possible. Even more curiously, the twin paradox also suggests that the fastest way to move into the future might be to leave it, to take a long, fast trip and return younger than everyone you left behind. Not through magic, not through machines that blink or twist, but through the cold, hard geometry of physics. And it's not just theory. If we had the energy, the materials, and the protection to build such ships, the aging gap would be measurable. Even now, in particle accelerators, we watch particles live longer simply because they're moving fast. Their own version of the twin paradox plays out in every beam of protons circling a ring. It's worth remembering too that time dilation is not something we feel. From the traveller's point of view, nothing is stretched or distorted. Their heart beats normally. Their thoughts unfold at the same pace. They don't feel time slowing down. It's only from the outside that the difference becomes visible. That makes it more eerie and more real. You can move through time without noticing, only to find, when you look around, that everything else has changed. This leads us into deeper territory, into questions about continuity and experience. If you return from a journey and find yourself in a different century, are you still part of your original story? Or have you become something else? A bridge between ages, a traveller from the past who no longer fits? There's no physics answer to that. Only personal ones. But what the twin paradox makes clear is that time, like distance, is not fixed. It's shaped by motion, by acceleration, by the choices we make about how and where to travel. And it's one of the few paths we know of that leads directly into tomorrow. Even if we learn to cross vast distances by bending space, or sliding into tomorrow through high-speed travel, there's one kind of journey that defies everything we hope travel could mean. A kind of place that isn't a place, but a boundary in the fabric of reality itself. It doesn't take you anywhere. It doesn't let you return. It simply erases the idea of back. A black hole is not a tunnel, or a pit, or even an object in the traditional sense. It's a region of space where gravity is so intense, so absolute, that nothing, not even light, can escape. And that phrase, not even light, isn't poetic exaggeration. It's a literal statement about the structure of space-time. Once something crosses the edge of a black hole, it's cut off. Not hidden behind a curtain or delayed by interference, but removed from the rest of the universe by the shape of space itself. That edge is called the event horizon. It's not a surface, not something solid or visible. It's a threshold, a limit. From the outside you can approach it forever and never quite touch it. But once crossed, escape becomes impossible. No rocket, no message, no burst of radiation can reverse the trajectory. The space-time inside is curved inward so dramatically that every possible path leads further in. To the outside universe, what falls in seems to freeze. Slowed by time dilation, light from infalling objects stretches and fades, taking longer and longer to reach us. A spaceship nearing a black hole might appear to hover just above the event horizon, red-shifted and dim, forever trapped in a moment. But from the point of view of the ship itself, time continues. It crosses the horizon in finite time, and once inside, it falls toward the centre, toward the singularity. The singularity is not a place in space. It's the end of space, a point, or perhaps something even stranger, where the known laws of physics break down. Density becomes infinite. Curvature becomes infinite. Time ends or becomes undefined. At least that's what our current understanding says. It's not just that we don't know what happens there, it's that our equations stop working. The singularity is where predictability dissolves. But the journey to that point is filled with strange transitions. As you fall toward the event horizon, time outside seems to speed up. Galaxies whirl through eons. Stars are born and die in the blink of your internal clock. Space becomes distorted. Directions lose meaning. The light from behind you curves around to enter your eyes from ahead. The inside of a black hole isn't just a deeper part of space. It's a different kind of space. One where the future is not where you are headed, but where you are falling. The pull of gravity is so intense that the very nature of time and space swap roles. Outside, you can choose to move forward or backward, left or right. But inside, the only direction left is inward. Not because you've lost control, but because the geometry no longer allows for anything else. Falling inward becomes as inevitable as aging. It's not a force pushing you. It's a path that can't be turned away from. This makes black holes one of the few places in the universe where space travel doesn't just become difficult, it becomes meaningless. There is no destination, no navigation. Once inside, the journey is a countdown, a slide toward a boundary that no one can describe. And this isn't some exotic fantasy at the edge of science. Black holes are real, observed, measured. We've watched stars orbit invisible centres. We've seen gravitational waves ripple out from collisions. We've even taken an image of the shadow cast by a black hole in a distant galaxy, an indirect portrait of the event horizon itself, carved out of light and silence. Some are the remnants of collapsed stars. Others, millions or billions of times more massive, sit at the hearts of galaxies. Their presence shapes the orbits of stars and the dynamics of galaxies. They eat matter and release energy, sometimes more violently than any other known source in the universe. And they are permanent, indestructible. Once formed, they only grow. You might ask, if nothing escapes, how do we know anything about what happens inside? The truth is, we don't. Everything we know about the interior of a black hole comes from theory, not observation. And that theory, powerful as it is, runs into limits. General relativity tells us what the structure should be like. Quantum mechanics tells us what particles and fields should do, but the two don't fit together smoothly at the singularity. This has led to decades of tension between theories. Black holes sit at the crossroads of physics, where gravity becomes so intense and scales become so small that our best descriptions fail to agree. This is where people hope a theory of quantum gravity will emerge, something that can reconcile the smooth curves of space-time with the jittery uncertainties of quantum fields. Until then, we live with paradoxes. One of the most famous is the information paradox. If something falls into a black hole, What happens to the information it contained? In physics, information is not just about books or memories. It's about the arrangement of matter and energy. According to quantum theory, information should never be lost. But if a black hole swallows everything and never releases it, that principle is broken. Stephen Hawking proposed that black holes might not be completely black. Quantum effects near the event horizon could allow particles to escape, what's now known as Hawking radiation. Over immense timescales, this radiation could cause black holes to shrink and eventually evaporate. But if they disappear entirely, what happens to the information? Is it lost forever? Scrambled? Stored in some holographic boundary? No one knows for certain. That's not just a theoretical problem. It cuts to the core of how the universe keeps track of itself. And black holes seem to sit just on the edge of where our understanding begins to blur. Despite all that, black holes are also tempting. People have asked for decades now whether they could be used as gateways or power sources, or even as time machines. There are speculative ideas, extreme wormholes, rotating black holes with ring-shaped singularities that might allow safe passage, but they rely on conditions and configurations that may not exist in nature. The most well-behaved black holes we know, Schwarzschild black holes, don't offer any way out. Once you're inside, you're not coming back. Some have suggested that information might be encoded on the surface of the event horizon itself. That black holes, strange as they are, might operate like cosmic vaults, storing everything that falls in on a two-dimensional surface in a kind of holographic memory. This idea, linked to the holographic principle, suggests that the universe itself may store more information on surfaces than in volumes. It's an idea still being explored, and its implications are far-reaching. What makes black holes so unsettling isn't just that they're powerful, it's that they redraw the map of what space can be. They tell us that location is not always accessible, that movement can end not in arrival, but in disappearance, that the universe, while vast and rich with destinations, also contains points of no return. You could imagine a civilization advanced enough to approach a black hole safely, to skim the edge of the event horizon, and use the time dilation to slow their own clocks. They might watch the universe evolve at hyperspeed, using the black hole as a window into the far future. But even that would have limits. Get too close, and you pass the point where watching becomes falling. And from there are no more choices. In that sense, black holes represent the end of navigability. They aren't paths to elsewhere. They're the places where elsewhere disappears, and yet they're part of the universe, part of the structure we might one day explore. They aren't edges of space, but folds, deep warps where motion turns inward. If you're looking for the ultimate one-way trip, there's nowhere else quite like them. From a safe distance, a black hole is a mathematical marvel, a gravity well with no bottom, a riddle at the heart of physics. But the moment the distance begins to shrink, and you move from observer to participant, the nature of that marvel changes. It becomes personal, less a mystery, more a fate. So what really happens if you fall in? The question isn't just theoretical, it's a thought experiment that shows how extreme physics starts to behave when you leave the normal world behind. Let's say, for a moment, you're in a spacecraft approaching a black hole. You're not tumbling or crashing, you're descending carefully in a controlled trajectory. The ship's instruments are still working, you're still receiving telemetry, light is still reaching your eyes, the black hole is ahead, invisible but present, and you're falling toward it, foot by foot, metre by metre. From a long distance away, your ship's descent appears to slow. As you approach the event horizon, observers far from the black hole would see your image redshift, stretched into lower and lower frequencies of light. It would fade, not because you're dimming, but because the light you're emitting is stretched into invisibility. Time, from their point of view, is slowing for you. Your clock ticks more slowly. Your heartbeat takes longer. Everything you do appears to freeze. But that's from their perspective. From your point of view, none of that's happening. Time continues normally. You don't feel slower. You don't see the universe speeding up. The ship's chronometers tick forward, The crew speaks at the same cadence. You feel gravity increase. You feel the pull growing stronger. Space starts to behave oddly. The stars outside the window shift. Their light bends. The sky warps. The direction of down becomes increasingly hard to define. As you cross the event horizon, something subtle and irreversible occurs. There's no bump, no flash. You don't pass through a wall or a surface. But inside the ship, the rules have changed. No matter how powerful your engines are, no matter how you thrust or steer, there's no direction that leads away from the centre anymore. Every possible future points inward. It's not that you've lost control, it's that the structure of space-time has reoriented itself. Forward in time now means downward in space. The singularity is not just where you're falling, it's when you're headed. This is where things start to depend heavily on the size of the black hole. If you're falling into a stellar mass black hole, a collapsed star a few times heavier than the Sun, the experience becomes fatal quickly. The gravitational gradient is steep. That means tidal forces, the difference in gravity from your feet to your head, become extreme. You're stretched vertically and compressed horizontally. The term for this is real, and not entirely poetic, spaghettification. The ship would begin to distort. If you're descending feet first, your legs accelerate more quickly than your chest faster than your head. The molecules holding you together stretch. Muscles and bones can't withstand the difference. The structure of the ship groans, bends, fails. Every part of you is pulled apart along the direction of descent. This process happens before you reach the singularity. It begins as you cross the event horizon and accelerates dramatically as you fall. Eventually your body becomes a line of particles, a string drawn out across a fraction of a second. You're torn not by heat or pressure, but by gravity's imbalance, a sheer difference in pull that becomes unbearable. But now imagine instead that you're falling into a supermassive black hole, the kind found at the centres of galaxies, with millions or billions of times the mass of the Sun. These black holes are vast. Their event horizons can stretch across entire solar systems, and their tidal forces at the horizon are gentle. You could cross into one of these without noticing. There would be no immediate stretching, no spaghettification. The gradient is shallow. You'd float calmly inward, passing the point of no return with barely a flicker. The ship's hull would remain intact. Your body would feel only the growing acceleration. Everything seems normal until it doesn't. Because the horizon, while quiet, still means what it always means. There's no escape. The journey to the centre is inevitable, and the closer you get, the more intense the gravity becomes. Eventually, even in a supermassive black hole, the tidal forces would become strong enough to distort and destroy, just much later than with a smaller one. But long before that, something else changes. Your connection to the outside world disappears. No signal you send can reach anyone. No light escapes. You're isolated not by distance, but by the very shape of reality. Communication ends. Observation ends. You exist inside a region where the rest of the universe can no longer interact with you. For all practical purposes, you've exited the cosmos. Inside the ship, clocks keep ticking. But the clocks mean less and less. Your future is already written, not in fate or prophecy, but in geometry. The singularity is in your future the same way tomorrow is. It's not a place you approach. It's a moment you cannot miss. This raises a deeper question. What happens at the singularity? The honest answer is, we don't know. Our current physics breaks down there. General relativity predicts an infinite curvature of space-time, a point of zero volume and infinite density. But infinities are a sign that the math has reached its limits. They're clues that a better theory is needed, one that includes both gravity and quantum mechanics. Some researchers believe that quantum gravity, whatever form it eventually takes, will resolve the singularity. Maybe it's not a point but a surface. Maybe it's not infinite but compressed. Maybe the structure of space-time changes in a way we don't yet understand. Until we have a theory that unites the big and the small, the singularity remains an open question. Another possibility, more speculative, is that the singularity might connect to something else, a bridge to another region of space-time. This is the origin of ideas like white holes or wormholes, but there's no evidence yet that such bridges form in real black holes. The simplest and most likely outcome, based on everything we've observed, is that the singularity is the end, and yet not everything that falls into a black hole is lost entirely. While the object itself may vanish, its effects linger. The black hole retains mass, angular momentum, and electric charge. These are known as conserved quantities, the external parameters that define the black hole. But the finer details, the information, are a different story. This leads back to the black hole information paradox. If you fall in, and your body contains information, patterns, memories, molecular arrangements, what happens to that information? Is it destroyed, preserved, transformed? Some physicists argue that information is stored at the event horizon in a kind of two-dimensional holographic field. Others think it's released during the slow process of Hawking radiation, encoded in subtle quantum correlations. Still others believe that the answer requires a radical rethinking of spacetime itself. Whatever the truth, the fact remains. Falling into a black hole isn't like falling into a hole in the ground. It's not a journey with an end point in space. It's a passage into a region where time, space, and cause collapse into each other. Once you cross the event horizon, you're on a one-way trajectory into an undefined future, a destination no one can describe. You don't just leave the world, you leave the shared structure that defines the world. The rules of before and after, here and there, lose their familiar shape. All that remains is a descent, not into darkness, but into the unresolvable. If black holes represent the most extreme barriers in space, regions where motion ends in inevitability, then quantum tunneling points towards something very different. A way of getting from here to there without travelling the space in between. A kind of leap, built not on brute force or curved geometry, but on probability. It doesn't look like motion, it doesn't obey classical rules, but it happens, and it's measurable. In classical physics, to go from one location to another, you must pass through every point in between. Whether you're walking across a room or flying to another planet, the path is continuous. Even if you jump, the arc of your motion still covers the distance. Every inch counts. Every step exists. But in the quantum world, particles don't always behave this way. Take a single particle, an electron say. Put it in a small potential well, a kind of trap made of energy. There's a barrier surrounding it, higher than the energy the electron possesses. According to classical physics, the electron shouldn't be able to escape. It doesn't have enough energy to climb out. But in quantum mechanics, the rules change. Particles are not tiny balls with exact positions. They're better described as waves, distributions of probability. Instead of existing at one precise location, a particle has a wave function, a spread-out description of where it might be found. That wave function can extend beyond barriers. And if it does, there's a small chance, calculated from the properties of the wave, that the particle will be found on the other side of the barrier. This is quantum tunneling. The particle doesn't go over the wall. It doesn't smash through it. It appears on the other side without having passed through the barrier in any classical sense. It's not teleportation. It's not magic. It's just a consequence of how quantum systems evolve. And we've seen it happen. In fact, much of modern technology depends on it. Tunnel diodes, flash memory, and scanning tunneling microscopes all rely on the ability of particles to tunnel through energy barriers. Without tunneling, nuclear fusion in stars would be impossible. Even in the Sun, the energy available is too low for protons to overcome their mutual repulsion, classically. But quantum tunneling allows them to get close enough to fuse, powering the star and, by extension, life on Earth. So tunneling is real. It's not a fringe idea or a speculative phenomenon. It happens all the time under the right conditions, but it doesn't happen with large objects, and it doesn't happen with people, at least not in any detectable way. That raises a question. Could this principle, leaping without crossing, ever apply to larger scales? Could we imagine a future where quantum tunneling becomes a form of travel? To answer that, we have to look at scale and probability. The likelihood of tunneling depends on the size and energy of the barrier and on the properties of the particle. For subatomic particles, the probabilities are reasonable. For molecules, they become tiny. For macroscopic objects, anything we can see or touch, they become absurdly small. The chance of a baseball quantum tunneling through a wall is, for all practical purposes, zero. Not zero in theory, but zero in practice. The time you'd have to wait for such an event to occur is many orders of magnitude longer than the age of the universe. It's not that it's forbidden, it's that it's irrelevant. But the idea still draws attention, because it points toward a different way of thinking about motion. In the quantum world, location isn't a single value, it's a distribution. Boundaries are not absolute. Energy barriers are not impassable. And cause and effect, the straightforward logic of A then B, becomes statistical. This has led some researchers to wonder whether similar principles might operate at larger scales, under special conditions. Could space-time itself allow for tunneling? Could the entire universe exhibit quantum behaviour under certain conditions, perhaps at the beginning of time, or in the presence of extreme gravitational fields? Some models of the early universe suggest that the Big Bang itself might have involved quantum tunneling, that the universe could have emerged from a quantum fluctuation, tunneling out of a prior vacuum state. If true, that would mean the cosmos itself was born from a kind of non-classical transition, a leap, not a movement. There's also interest in whether tunneling could allow black holes to evaporate more quickly than Hawking radiation predicts. If particles can tunnel out of the event horizon under certain quantum conditions, it could change how we understand black hole lifespans. But what about travel? Could we ever use tunneling to cross space without covering the ground in between? In theory, there are concepts like quantum teleportation, but this is not movement in space. It's the transfer of quantum information, entangled states and measurement outcomes, from one location to another. It requires classical communication channels and shared entanglement. No object actually moves. No mass or energy crosses space instantaneously. The name is misleading. Quantum teleportation is about correlation, not transport. Still, the quantum world offers models of interaction that defy classical structure. Entangled particles can exhibit correlations across distance, not because something travels between them, but because their properties are linked in a way that transcends separation. It doesn't allow faster-than-light messaging, but it does hint at deeper connections in the fabric of reality. If these connections could be harnessed, if we ever discover a way to manipulate quantum states across space on large scales, it might lead to forms of communication or interaction that don't rely on classical motion. Not travel, perhaps, but something like presence, the beginning of a new kind of reach. This leads into the speculative territory of quantum gravity. If space-time is quantized, made up of discrete units, then perhaps position itself is uncertain at the deepest level. Maybe geometry isn't continuous. Maybe large-scale motion could one day include shortcuts built not from tunnels or warp fields, but from uncertainty itself. But even if we never scale up quantum tunneling, its existence matters. It shows that the boundaries we treat as solid, in space, in energy, in logic, are not absolute. That the universe allows for exceptions, that sometimes the way forward is not over or around, but simply through, in a way that no classical path could allow. It also reminds us that our experience of reality is shaped by limits, not just of speed and energy, but of perception. At the quantum level, particles don't behave like objects. They don't have trajectories. They're governed by probabilities described by functions, collapsed by observation. And in that world, movement doesn't require motion. Transition doesn't require passage. So while quantum tunneling may never carry a human across the stars, it tells us something fundamental about what space is and what it's not. It's not a hard grid or a fixed volume. It's a field of possibility. A domain where, under the right conditions, even the impossible becomes likely enough to matter. Quantum mechanics doesn't just introduce uncertainty into the way particles move or interact. It introduces a kind of branching, a set of possibilities that exist not in the imagination, but in the equations. When a particle can be in more than one state, and its wave function evolves to include all of them, measurement forces a choice. And one interpretation of what happens during that choice is that it's not a choice at all, that every possible outcome occurs somewhere. This leads into the many worlds interpretation, a view of quantum mechanics that suggests instead of probabilities collapsing into a single event, reality splits. Every time a quantum event happens, a particle goes left or right, an atom decays or doesn't. The universe divides. In one version, one result. In another, a different one. The result is not one timeline, but a branching tree of possibilities. A multiverse. To most people, this sounds like science fiction. A collection of parallel worlds, each with its own version of events, each following a different path. But this interpretation wasn't dreamed up to make stories interesting. It emerged from attempts to understand quantum mechanics without invoking collapse or randomness. If the wave function is real, if it describes the world accurately, then all of its components must be equally valid. And if they're all valid, then they must all happen. In this view, when you measure a quantum system and see one outcome, there are other versions of you, in other branches of the universe, seeing the other outcomes. You don't switch between them. You don't choose. They all unfold side by side, inaccessible but equally real. And if that's true, then the universe is far larger, not just in size, but in scope, than we usually imagine. Because every interaction, every choice, every quantum event would spawn a new divergence. The number of branches would be astronomical, infinite perhaps. Every version of history, every road not taken, played out in full somewhere beyond our reach. This doesn't mean anything goes. It's not a license for fantasy. The branching follows the rules of quantum mechanics. It's constrained by the mathematics. You won't find a branch where physics stops working, or where logic breaks down. But within those constraints, the variety is staggering. And that brings us to a new kind of distance, not between stars or galaxies, but between realities. If these alternate universes exist, they're not located somewhere else in space. They're not across the room or on the other side of a portal. They're part of a larger structure, a space of states, not of places. They're not out there. They're alongside, in a sense we don't have normal language for. Could we ever travel between these branches? That's where the theories become speculative. Right now, there's no known mechanism for crossing from one branch to another. No tunnel, no shortcut, no signal. In the many worlds view, each universe evolves on its own trajectory, with no overlap. Decoherence, the process that separates the branches, is fast and irreversible. Once the wave function is split, the branches are causally disconnected. But still, the question persists. If the universe is full of versions, of outcomes and timelines we never experienced, is there a way to reach them? Not just theoretically, but physically. So far, nothing in physics allows for that. But it hasn't stopped people from looking. Some interpretations of quantum gravity suggest that space-time itself might be emergent, not a fundamental backdrop, but a result of quantum entanglement. If that's true, then maybe the separation between branches isn't absolute. Maybe, at the deepest level, there's a shared structure that could be manipulated. Others have proposed that under extreme conditions, black holes, high-energy particle collisions, cosmological boundaries, there might be ways to influence which branch becomes realized. Not to jump between worlds, but to bias the probabilities, to steer reality, rather than leap across it. None of these ideas are confirmed. They're frameworks, not findings, but the mere fact that physics allows us to imagine them shows how far our understanding has come. The universe is no longer a single fixed story. It's a set of possibilities, governed by laws that allow for uncertainty, superposition, and divergence. There are other kinds of multiverse theories too. Some emerge from cosmology. The inflationary model of the early universe suggests that our observable cosmos is just one bubble in a much larger inflating space. Each bubble could contain different physical constants, different particles, different structures. These pocket universes would be causally disconnected. We could never reach them, and they could never reach us. But they'd be real, in the same sense that ours is. This kind of multiverse is less about quantum mechanics and more about initial conditions. If the universe is infinite, or if it inflated eternally, then there may be regions of space that are forever separated. We see a limited part of the whole, not because the rest doesn't exist, but because light hasn't had time to reach us from those regions, and never will. There's also the string theory landscape. In that framework, there are an enormous number of possible vacuum states, ways that extra dimensions and fields could be configured. Each configuration leads to a different set of physical laws. If string theory is right, and if the universe explores all these configurations, then the multiverse would be a vast collection of domains, each with its own version of physics, not just alternate outcomes, alternate realities. Again, this raises the question, could we ever cross between them? Probably not. The barriers between these universes are not spatial. They're defined by field configurations and energy states. To cross from one to another would mean changing the very nature of space-time, reshaping the fields that give particles their mass, the constants that govern forces, the topology of dimensions. It's not just impractical, it might be meaningless. But that doesn't mean the idea has no consequences. In fact, the multiverse can affect how we interpret what we observe. If there are many universes, each with different properties, then the fact that we live in one suitable for life may not be surprising. We couldn't observe a universe where life is impossible, so we find ourselves in a place that allows observers. This is called the anthropic principle. It's not satisfying to everyone. It feels like giving up on explanation. But in a multiverse, some outcomes don't need fine-tuning. They just need selection. We see what we can see because it's one of the few versions where seeing is possible. That brings us back to travel. If we're confined to a single branch, a single bubble of reality, then space remains our only frontier. We can go farther, go faster, explore what's out there. But if the multiverse is real, then there's another kind of reach we can't yet access. A reach across versions, across outcomes. Even if we never cross that boundary, it's worth thinking about what it means. Every choice, every measurement, every interaction could be part of a larger structure, a web of possibilities. We experience one thread, others go untravelled, but they may still exist. This isn't just an abstract idea. It changes how we think about paths, about what's fixed and what's open, about whether the future is something we make or something that already exists in many forms. In a universe like that, exploration isn't just about motion. It's about awareness, about understanding the shape of reality and how much of it lies outside our reach, not because of distance, but because of divergence. After walking through the territory of alternate realities, quantum probabilities, and cosmic branches, it's easy to wonder whether we might bypass space entirely, whether instead of crossing it, with engines, trajectories, or bending, we could simply vanish from one point and appear in another. The idea of teleportation has been part of science fiction for decades, but in the real world that word means something far more precise, far more limited, and far more revealing. Teleportation, in scientific terms, does not refer to moving objects across space instantly. It doesn't involve blinking out of existence and reappearing somewhere else. In fact, nothing physically travels faster than light. What quantum teleportation does involve is information, specifically the complete quantum state of a particle, its exact configuration, its wave function, being transferred from one place to another without the particle itself making the trip. That distinction matters. In quantum teleportation, what moves isn't the object, it's the identity. The full description of the particle at one location is destroyed, and a copy is reassembled at another. But to make this happen, a few ingredients are required. First, you need two particles that are entangled. Entanglement is a special quantum connection between particles, where the state of one is linked to the state of the other, no matter how far apart they are. If you measure one, the state of the other is immediately determined, not because a signal travels between them, but because the system as a whole contains correlated information. Once you have an entangled pair, let's call them A and B, and you bring in a third particle C, whose state you want to teleport, you can perform a special joint measurement on C and A. That measurement doesn't tell you everything about C's state. Instead, it entangles C and A in a way that depends on C's original properties. The result of that measurement is random, but it contains just enough information, when sent via a classical channel, for someone at particle B's location to reconstruct C's original state. The key here is that the original state of C is gone, wiped out by the measurement. But particle B now contains that same state. It has become the new version of C, not a clone, not a duplicate, but the same quantum configuration, now located elsewhere. This process has been demonstrated many times in the lab. Photons, electrons, even atoms have been teleported over short distances, meters in some cases, kilometers in others. The technique is precise, repeatable, and growing more sophisticated. It's part of what makes quantum communication and quantum computing possible. But despite the name, it's not anything like the teleportation we imagine from movies. You can't teleport a chair or a book or a person. There are limits, severe ones. For one, teleporting a quantum state requires prior entanglement. That means the destination must already have a particle entangled with one at the source. Entanglement has to be created ahead of time. You can't just pick a destination at will. Second, the measurement that allows teleportation requires destroying the original state. This isn't optional, it's part of how quantum systems behave. Measurement is invasive. It collapses the wave function, so you can't copy and paste a quantum state. You can only cut and paste, and perhaps most importantly, the process depends on classical communication. The outcome of the measurement must be sent through normal, slower-than-light channels to the receiver. That means teleportation can never be used for faster-than-light travel or messaging. The reconstruction of the state at the destination requires instructions from the source, and those instructions can't outrun light. So, even though the transfer of identity happens in a non-local way, the process itself is still grounded by the speed of light. It doesn't allow violations of causality or shortcuts across time. Now, the question often follows, could this be scaled up? Could you teleport something bigger, a molecule, a bacterium, a person? In theory, the answer isn't an outright no, but in practice the barriers are immense. To teleport a human being, you'd need to extract and encode the full quantum state of every particle in their body. That includes not just position and momentum, but spin, entanglement, and correlation with everything around them. The number of particles is on the order of 10 to the 28. The information required to describe them would exceed any conceivable storage or processing system. Even if you could solve that, you'd face the issue of destroying the original. Teleportation, as we understand it, involves erasing the original state when the measurement occurs. You wouldn't be moving a person, you'd be disassembling them down to quantum dust and reconstructing their quantum state elsewhere, assuming everything worked perfectly. Which leads to the deeper question. Even if it were possible, would the result still be you? From a physics standpoint, it might be. The quantum state would be identical, but consciousness, identity, memory. These aren't just physical configurations, they're experiences. Teleportation might replicate your structure, but it might not preserve your continuity. That's not a scientific conclusion, it's a philosophical one, but it matters when we start thinking about using quantum processes for real travel. So, for now and likely forever, quantum teleportation remains a tool for transmitting information, not matter, not minds. It's already finding applications in secure communication. Quantum key distribution, for example, uses principles of entanglement to detect eavesdropping. In the future, quantum networks may rely on teleportation to move information between nodes without direct transmission. It's also possible that teleportation could play a role in building distributed quantum computers, systems where parts of a computation occur in different places, with quantum states transmitted between them. But again, these are systems of information, not of transport, not of presence. Still, the concept is revealing, because it shows us that identity, at least in quantum terms, can be transferred. Not the object, but the configuration. Not the mass, but the state. That distinction between what a thing is and what describes it is at the heart of modern physics, and it opens the door to broader questions. Could a civilization someday master quantum state transfer on macroscopic scales? Could it build replicas of objects, or people, from instructions alone? Could it use quantum information as a way of preserving or transmitting experiences, all speculative, all far from realization? But each idea pulls us deeper into what it means to move through space, or to escape it altogether. Teleportation isn't a method for crossing the universe. It won't help us reach Alpha Centauri or step through a portal. But it offers something else, a glimpse into how the universe handles change, transfer, and continuity. It reminds us that not all movement is physical, that sometimes what matters is what gets preserved and what gets left behind. When the conversation moves from entanglement to teleportation, from time dilation to warping space-time, it's hard not to feel the shadow of fiction looming nearby. Not because the science is wrong, but because the ideas being discussed have, for decades, lived in two parallel spaces. One, the rigorous world of physics. The other, the imaginative world of speculative storytelling. And somewhere between those two, in a space where mathematics and wonder overlap, is where science and science fiction start to mirror each other more than either side usually admits. The boundaries between them aren't as sharp as people might think. Many of the technologies we take for granted today first appeared in fictional worlds. The idea of a satellite predates the launch of the first one. Tablets, voice interfaces, video calls, all imagined long before they were engineered. But fiction has always moved faster than science, not because it predicts, but because it permits. It allows ideas to be tried without testing, explored without funding, believed without evidence. Fiction asks, what if? Long before science answers, how? In the context of space travel and universal exploration, science fiction has long been a sandbox for impossible journeys. Characters leap across galaxies, bend time, step into other dimensions. Ships disappear from one location and arrive at another with no regard for the speed of light, no concern for time dilation or energy requirements. Whole civilizations exist beyond black holes or between timelines, and often the narrative doesn't pause to explain the physics, because it doesn't need to. The rules are flexible, as long as the story remains grounded in its own logic. But within those imagined journeys, there's often a spark of real theory, a real paper, a real scientist who once asked a question that led to an equation. Many of the most enduring science fiction ideas have a scientific root, even if that root has grown into something unrecognizable. Wormholes, for example, began as a solution to Einstein's equations, a mathematical curiosity. Warp drives have been described in actual physics papers, with equations outlining how space-time might be compressed and stretched. Even time travel in the forward direction has been experimentally confirmed in limited ways. And so, when science fiction introduces a new concept, a transporter, a faster-than-light engine, a stable wormhole, it often reflects an underlying curiosity that already exists in science. The fiction is a sketch, and the science is an attempt to fill in the details. There's a feedback loop between the two. Scientists read science fiction. Many physicists were inspired by novels or films as children. The sense of wonder, the belief that the universe could be explored in ways beyond our current reach, that's where a lot of careers begin. And once those scientists begin doing real work, they often return to those fictional ideas, wondering how close we could come to making them real. Still, there are limits. A concept's presence in fiction doesn't make it feasible. Teleporting a starship with crew and cargo is still physically implausible. Folding space like a sheet of paper requires exotic matter we don't know how to produce, in quantities we can't manage. Living indefinitely in alternate timelines, or communicating across galaxies in real time, all confront hard boundaries: energy, information, causality. Science fiction often sidesteps these limits by invoking advanced civilizations, unknown materials, or future breakthroughs. That's not dishonest. It's part of the genre. Fiction doesn't owe anyone a blueprint, but in science, those gaps have to be filled before a concept becomes viable. It's not enough to want it to work. It has to be possible within the known laws of nature, or those laws have to be revised, and the revision needs evidence. That doesn't make science cold or unimaginative. In fact, it's often the opposite. The process of trying to bridge the gap between what we can describe and what we can imagine is deeply creative. When a physicist writes an equation for a warp bubble, or calculates the tidal forces inside a hypothetical wormhole, they're not trying to write a script. They're trying to test the boundaries of reality. Sometimes that testing leads to surprises. The Alcubierre warp drive, a theoretical model for faster-than-light travel, came not from science fiction, but from an attempt to manipulate Einstein's equations in a new way. It describes a region of space-time compressed in front of a vessel and expanded behind it, allowing the ship itself to remain stationary while the bubble moves. The math works, with enormous caveats. It requires negative energy, something we don't know how to generate or contain. The amount needed is staggering. But the point is, the idea went from fiction to formula. Other examples include rotating black holes that might allow closed time-like curves, a mathematical term for paths through space-time that loop back on themselves. Again, these arise from general relativity, not from storytelling, but their implications have become part of fiction, and the fiction, in turn, keeps the ideas alive. There's also the role of paradox. Many science fiction stories explore what happens when causality is broken, when effects precede causes, when information loops back on itself, when travellers meet their own past. These aren't just narrative tricks. They're reflections of real problems that appear in some solutions to Einstein's field equations. Physicists use paradox not just to entertain, but to test consistency. If a theory allows for a paradox, does it still make sense? Can it still describe the world? In this way, fiction becomes a kind of lab, a virtual environment where impossible conditions can be simulated, not with code, but with plot. And if the simulation holds, if the story doesn't collapse under its own weight, it can suggest directions for real inquiry. But perhaps the most important role science fiction plays is in reminding science of its scale. Not its scale in terms of numbers or equations, but in human terms. What does it mean to travel far from Earth? To meet a version of yourself from another timeline? To live long enough to see centuries pass? These aren't technical questions. They're experiential, and fiction gives them shape. When we think about crossing the universe, or building ships that manipulate space-time, or using entangled particles to communicate across star systems, we're not just asking, is it possible? We're asking, what would it feel like? And that question, often dismissed as soft, is actually central. Because until something is experienced, it remains abstract. Science is good at describing what happens. Fiction is good at describing what it means, and when the two work together, not as opposites, but as collaborators, the result is something larger than either one alone. Of course, not all science fiction aims to be accurate. Some stories use scientific language loosely, or ignore known limits entirely. That doesn't make them less valuable. The genre is broad. Some of it is predictive, some of it is cautionary, some is purely metaphorical. But in every case it reflects our curiosity, our sense that the universe is bigger than we can currently reach. So while science keeps asking questions like, how much energy would a warp bubble require? Or, how does entanglement scale across systems? Fiction keeps asking, what if it worked anyway? And together they form a kind of loop. Ideas moving from lab to page and back again. In the end, the intersection of science and science fiction is not about accuracy. It's about possibility. The fact that so many real-world physicists spend their lives trying to understand ideas that once lived only in novels or films says something about how imagination works. It doesn't sit outside science, it fuels it. And that may be the most important point, because before we can build a thing, we have to imagine it. Before we can test it, we have to believe it's testable. Before we cross the stars, we have to think of ways we might do it. And most of those ways will begin, not in labs, but in stories. After exploring concepts like warp drives, wormholes, quantum teleportation, and alternate universes, a question quietly surfaces beneath all the curiosity. Even if the theory works, can we actually do any of this? And more specifically, what would it take in practical physical terms to build the machinery for such travel? This is where the conversation about space and time, once abstract and exciting, runs into a very grounded wall: energy and engineering. There's no shortage of ideas for faster-than-light travel or manipulating space-time, but when you start calculating what these ideas would actually require, not in science fiction, but in reality, the numbers become overwhelming almost immediately. Take the Alcubierre warp drive as an example. As a concept, it's elegant. The ship doesn't move through space. Instead, space itself is compressed in front of the ship and expanded behind it. The bubble of space-time moves, and the ship rides inside. From the outside, the ship might appear to move faster than light, but locally nothing exceeds the speed limit. On paper, it's fascinating. It uses general relativity's own equations to describe how the curvature of space might be used as a propulsion method. But then you get to the part of the paper that talks about energy. In its original form, the warp drive would require the mass energy equivalent of a planet, possibly a gas giant, and not just in any form. It would need to be negative energy. This isn't energy that's just hard to get. It's energy that might not exist in usable amounts. Negative energy, or exotic matter, has been theorized in small, highly specific quantum conditions, but producing it, storing it, shaping it, that's an entirely different challenge. The Casimir effect, a quantum phenomenon observed between very close uncharged conducting plates, does create a form of negative energy density, but only in minuscule amounts. Not enough to move a grain of sand, let alone a ship. Even revised versions of the warp drive, which attempt to reduce the energy demands by clever mathematical changes, still require exotic conditions far beyond our current abilities. The engineering challenges alone, building a vessel that could withstand warped space-time, controlling the shape and boundary of the warp bubble, and ensuring stability, are completely outside anything modern technology can handle. The same applies to traversable wormholes. The equations for such structures exist. In theory, a wormhole could connect two distant regions of space, allowing near-instant travel between them. But to keep a wormhole open, to prevent it from collapsing under its own gravity, you'd need matter with negative energy density again. A lot of it. There's no known way to stabilize a wormhole with ordinary matter. Every natural gravitational structure we've observed behaves predictably under mass and energy. It attracts, it collapses, it follows well-understood rules. Wormholes, if they can exist at all, would need to defy those behaviours. Even if you could gather the right materials, there are other challenges. Space-time isn't something you can easily manipulate like fabric. It's defined by the presence of energy and mass. To bend it significantly, you need enormous quantities of both. To shape it with precision, you need control systems that don't exist yet. Systems that can operate on scales, orders of magnitude beyond anything built so far. This leads to one of the biggest barriers in making theoretical travel ideas real: energy scale. Most futuristic travel proposals involve energies comparable to stellar events, not because the ideas are flawed, but because space itself is rigid on large scales. Bending it, warping it, opening holes in it, these aren't actions you can take lightly. You're not moving through air or water. You're trying to reshape the very thing that defines position and movement. To escape Earth's gravity alone, we already burn vast quantities of fuel. A single launch requires hundreds of tons of propellant. To reach other planets in our solar system, missions take years of planning, trajectory correction, and fuel efficiency management. And those are relatively nearby destinations. Once you talk about other stars, the scale becomes astronomical. Even travelling at 1/10 the speed of light, far slower than warp drives or wormholes would imply, would take almost 50 years to reach Proxima Centauri, the nearest star. But accelerating a spacecraft to that speed requires staggering amounts of energy, and then you have to decelerate at the other end. Every increase in velocity increases the energy demands exponentially. Kinetic energy scales with the square of velocity. That means doubling the speed quadruples the energy needed. Some proposals suggest using fusion, antimatter, or light sails pushed by lasers as propulsion systems. Each of these comes with its own engineering hurdles. Fusion is not yet practical for continuous propulsion. Antimatter is extraordinarily difficult to produce and store. Even tiny amounts require particle accelerators and vast energy inputs. Light sails are promising, but require powerful lasers, likely based in orbit or on the moon, and careful beam management over enormous distances. Even assuming one of these propulsion methods could be developed, we'd still face structural problems. Moving at relativistic speeds through space means encountering dust and gas at incredibly high relative velocities. A single grain of sand hitting a ship at half the speed of light could be catastrophic. Protecting a craft from such impacts would require shielding far beyond anything ever flown, or it would require clearing a path, which adds even more complexity. Then there's heat. At near-light speeds, interstellar gas becomes a source of intense friction and radiation. The ship could heat up from the compression of particles against its front surface, requiring thermal management systems that must function continuously and flawlessly for years. Communication poses another limit. As distance increases, the delay in sending and receiving messages grows. Even with light-speed communication, a message to a ship halfway to another star could take years to arrive. Real-time control or assistance becomes impossible. The vehicle must be autonomous, self-correcting, and prepared for complete isolation. And these are the engineering challenges for sublight travel. The more exotic forms, warping, tunneling, bridging, multiply the problems. We'd need new physics, new materials, new forms of energy generation, and completely new control systems. That doesn't mean these things are hopeless. It just means that the path from theory to practice is longer than most people realise. In science fiction, ideas are constrained by plot. If the story requires a warp jump or a stable wormhole, one appears. But in reality, every new capability builds on existing technology. Every leap has to be tested, modelled, verified. This is where the real-world scientists come in. Theoretical physicists continue to write papers exploring what's possible under current models. Experimental physicists try to verify those models. Engineers work to scale up what's known. But none of them are starting from scratch. They're standing on hundreds of years of progress, with tools that are advancing but slowly, relative to the scale of what's needed for interstellar travel. Another complication is energy storage. Even if you could produce the necessary energy, how would you store it on board? Chemical fuels are too weak, batteries are too heavy, nuclear energy helps, but creates shielding and safety issues. High-density energy storage remains one of the most difficult engineering problems across all fields. Even for basic tasks like powering spacecraft systems for decades, lights, sensors, navigation, power generation becomes a concern. Solar panels become less effective the farther you move from the sun. Radioisotope thermoelectric generators have limited lifespans. Fusion and antimatter again are theoretical in this context. So we're left with a sobering truth. The universe allows for incredible possibilities, on paper. But turning those possibilities into real engines, ships and journeys remains out of reach. Not because we lack imagination, but because we haven't solved the energy and engineering. And yet, slow progress continues. Every launch, every probe, every improvement in propulsion or materials brings us one step closer. Not to warp drives, perhaps, but to pushing farther. Every solution we develop for efficiency, autonomy, shielding, or propulsion gets folded into the next generation. That's how space travel has always worked. Not in leaps, but in layers. The spacecraft that now exits our solar system, like Voyager 1, was built with decades of technology behind it. And the ones that come next will build on even more. Maybe one day, the energy requirements won't be as steep. Maybe we'll discover new physics that changes the landscape entirely. But until then, exploration remains a challenge not of theory, but of execution, of solving real, physical problems. When we talk about exploring the universe, the biggest obstacle is often phrased in terms of distance. Stars are far away, galaxies are even farther. The visible edge of the universe is billions of light years from where we are now. On the surface, it seems like a simple problem, a matter of getting from point A to point B. But that framing assumes something that might not be quite right. It assumes distance is a fixed quantity, something absolute and straightforward, something you can measure with a ruler that doesn't change. But space, as physics understands it today, doesn't work that way. Distance isn't just a line between two places, it's a property of the geometry of space-time. That geometry can curve, it can stretch, it can expand, and in some interpretations of cosmology, distance might not even be real in the way we typically imagine it. Start with expansion. The universe is growing, not into something, but within itself. The fabric of space isn't static, it's dynamic. Galaxies aren't simply moving away from us because of some initial explosion. Space itself is expanding between them. This has been observed through redshift, the stretching of light from distant galaxies. The farther away something is, the more its light is redshifted. Not because it's moving faster in a traditional sense, but because the intervening space has stretched more since the light was emitted. This changes the meaning of distance. If you ask how far away a galaxy is, the answer depends on what you mean. Its proper distance now, the distance if you froze expansion and measured it today, might be one value. The light travel distance, how long light took to get here, gives a different number. And in cosmology, there are even more definitions: co-moving distance, luminosity distance, angular diameter distance. They all describe different aspects of separation, shaped by the geometry of space-time and how it evolves. So when we say something is 1 billion light years away, we're simplifying. We're compressing a lot of complex, changing geometry into a single number. But in reality, that number isn't fixed. The space between us and that galaxy is growing every second. Light travelling toward us from that galaxy moves through a stretching path. It takes longer, it covers more space, and the more time passes, the more that distance grows. That's one reason why some galaxies are already unreachable, even if we had ships that could move at the speed of light. The expansion rate of the universe is accelerating, driven by dark energy. That means more and more of the universe is receding from us faster than light. Not because the galaxies are moving faster than light in space, but because space itself is expanding faster than light over large enough distances. This doesn't violate relativity. It's how general relativity describes large-scale spacetime dynamics. But it does mean that some places, even if they emitted a signal now, could never reach us. And if we sent a signal to them today, it would never arrive. That's what cosmologists mean when they talk about a cosmic horizon. There's a boundary beyond which events cannot affect us no matter how much time passes, not because of limitations in technology, but because of the structure of the universe itself. And this again challenges the idea that distance is just how far something is. It's also about when and how space-time behaves between here and there. Some researchers take this even further. In certain theories of quantum gravity, the as yet undiscovered framework that would unify general relativity and quantum mechanics, space might not be fundamental at all. It might be emergent. That is, space could be a property that appears from deeper processes, like temperature emerges from molecular motion. You don't need temperature in the equations of quantum electrodynamics. But when enough particles come together, temperature becomes a useful concept. If space is emergent, then distance is too. What we experience as location, separation, and movement might be the large-scale result of something more fundamental: information, entanglement, or network structure. In some proposals, such as those based on holography, the idea is that all the information contained in a volume of space can be represented on its boundary. That's not just a mathematical trick. It's a real physical proposal that underlies much of modern thinking about black holes and entropy. In those models, the volume of space isn't truly three-dimensional. It's encoded in two dimensions, like a hologram, and the space we live in is, in some sense, a projection of deeper informational relationships. If that's true, then talking about distance, the way we do now, might be like talking about up and down on a flat computer screen. It makes sense in context, but it's not fundamental. There's also the notion of relational space. In classical physics, space is a stage on which events happen. Objects move through it, interact within it. But some interpretations of quantum mechanics suggest that space is not a container, but a result of relationships, that particles are not located in space. Their relationships define space. In other words, what matters isn't where something is, but how it interacts with everything else. The structure of those interactions defines the apparent geometry. That might sound abstract, but it leads to practical consequences. It means that if you change the network of relationships, through entanglement, for example, you might change the effective distance between things. Some theoretical proposals even suggest that entanglement is the glue that holds space-time together, that the reason space has structure at all is because of how quantum systems are entangled. This view is still being explored, but it hints at a possibility, that if you could control entanglement at a large scale, you might be able to affect distance in a way that bypasses traditional motion. This wouldn't be movement in the sense of flying from one star to another. It would be a reconfiguration of relationships. If distance is not a constant but a feature of connections, then the right change in connection might reduce distance. This all remains speculative. None of it gives us a working engine or a shortcut through space-time. But it does shift how we think about the challenge. If distance is not always what it appears to be, then the problem of crossing it becomes different too. Even in general relativity, the idea of a straight path, a geodesic, depends on the curvature of space-time. Light always follows a geodesic, but that path can bend, twist, or even loop depending on the gravitational field. That's how gravitational lensing works. A massive object like a galaxy can bend the light from a more distant object, creating arcs or multiple images. The light still travels the shortest possible path, but in curved space that path is curved. So even now in a universe we can observe, distance isn't a straight line. It's shaped by the mass and energy in the environment. If you put more mass in one place, the paths change. The distances change. On cosmic scales, we also see voids and filaments, large structures where matter is clumped or spread out. These affect the motion of galaxies. The path of light and the distribution of gravitational fields. Space isn't uniform, it's textured, and that texture affects what distance means. Then there's time. In relativity, time and space are not separate. They're parts of a single fabric, space-time. And when time is affected, so is space. The presence of gravity slows time. That's been measured. GPS satellites account for it constantly. But if time moves at different rates in different places, then the intervals between events, the space-time separations, become more complex. You can't describe location without also describing when. So in a relativistic universe, distance and duration are inseparable. And since time itself is affected by speed, gravity, and motion, there's no absolute scale for how far something is. There's only how far in your frame of reference. In another frame, that same journey might look shorter or longer. This brings us back to the idea that distance is a perspective, a measurement that depends not only on geometry, but on how you're moving, how you're measuring, and what you're comparing it to. That may sound limiting, but it can also be freeing. If distance isn't fixed, maybe it can be changed, not by covering ground, but by adjusting perspective, not by moving faster, but by understanding what makes things far to begin with. For now, those ideas remain part of the theoretical frontier. We can't yet manipulate space-time curvature at will. We can't rewire entanglement across light years. But the fact that distance behaves this way, that it isn't always what it seems, offers a new kind of hope. Not the hope that travel will be easy, or that shortcuts will suddenly open up, but the hope that the universe might have options we haven't yet considered. That the barriers between us and the stars are not just vast stretches of empty space, but puzzles. And puzzles, once understood, can sometimes be solved. We often talk about space travel as if we're standing still, looking out, waiting to move. The stars are fixed, the planets are where they are, and we imagine ourselves as the ones who must do the travelling. The rockets, the probes, the ships. They're all extensions of our desire to move outward. But there's a quiet detail that often goes unspoken. The universe is not stationary. It's never still. Everything is in motion already, including us. Even if you're sitting quietly in a chair, you're moving. The Earth rotates on its axis at roughly 1,600 kilometers per hour at the equator. At the same time, it orbits the Sun at about 107,000 kilometers per hour. The Sun itself is moving too. It's orbiting the centre of the Milky Way galaxy at about 828,000 kilometers per hour. And the galaxy isn't fixed either. The entire Milky Way is moving through space, relative to the cosmic microwave background, at roughly 2.1 million kilometers per hour. When you combine these motions, the result is that every second we are travelling enormous distances through space without even realising it. We don't feel it because the motion is smooth. There's no acceleration to detect, no bump or jolt to remind us. We're inside the system, carried along with it. In many ways, our experience of motion is relative. You feel movement when something changes, when the car speeds up or slows down, when the elevator starts to rise. But constant motion, especially when shared by everything around you, feels like rest. It's only when you look outside your frame, at the stars, at distant galaxies, that the motion becomes visible. That perspective shift raises an important point. The act of travel is often defined by contrast. If you're on a train and the landscape moves past you, you're travelling. If you're in deep space and there's no reference point, motion becomes harder to define. Einstein made this clear in his work on relativity. There's no absolute frame of rest in the universe. Everything is in motion relative to something else. So in that sense, we're always travelling. The question is, relative to what? Even the very expansion of the universe contributes to our movement. Space itself is stretching, and as it does, it carries galaxies farther apart. This isn't motion through space in the usual sense. It's motion of space itself. If you picture galaxies as dots on the surface of an inflating balloon, Then as the balloon expands, the dots move apart. Not because they're crawling along the surface, but because the surface itself is growing. This expansion is measured relative to the cosmic microwave background, the faint afterglow of the Big Bang. It's the oldest light we can observe, and it gives us a kind of reference frame. Against this background, scientists can measure our velocity, and what they find is that we're not just drifting, we're sailing through the cosmos at incredible speed. None of this movement is something we cause. It's not chosen, it's inherited. The motions come from gravitational interactions, orbital dynamics, the structure of the early universe. And while we can't steer them, they shape our experience of time and distance more than we might expect. For example, the direction and speed of our movement affect how we observe cosmic phenomena. Light from stars ahead of us is slightly blue-shifted. Light from stars behind us is slightly red-shifted. These effects are subtle, but measurable. Our motion also causes the cosmic microwave background to appear slightly warmer in the direction we're heading and slightly cooler behind us. A dipole pattern that provides one of the most precise measurements of our cosmic velocity. This constant motion has consequences. It affects navigation in space. It influences how long signals take to reach us. It changes the timing of pulsars, the apparent positions of stars, and the measurements astronomers make when calculating distances. The cosmos isn't static, and our position within it is never fixed. But here's the more intriguing idea. If we are always moving, through space, through the galaxy, through the universe, then maybe exploration is happening all the time, just not in the way we imagine. A spacecraft doesn't always have to move towards something. It can wait, and let the universe move toward it. Over long enough time, that can make a difference. The solar system completes one orbit around the galactic centre roughly every 230 million years. That orbit brings us through different regions of the galaxy, areas with different densities of stars, different radiation environments, different gravitational fields. Even without travelling deliberately, we pass through space that is constantly changing. Dust clouds, radiation belts, stellar winds, all of these vary with location. Our cosmic neighbourhood is not a constant. It shifts, it evolves, and our motion through it exposes us to new conditions. That motion can even affect the long-term evolution of Earth. Some researchers have proposed links between our galactic orbit and cycles of extinction or climate. The evidence is not conclusive, but the idea is simple. If the solar system passes through a denser region of the galaxy, with more stars and more potential supernova, Earth could experience higher radiation levels. That might influence biology, or it might increase the odds of comet impact by disturbing the Oort cloud. All of this is to say, space travel is not only about propulsion, it's about movement, and movement doesn't have to come from engines. Sometimes the most profound journeys are passive. We're carried by the structure of the cosmos itself. In a way, that reframes the problem. If the universe is always moving, then maybe our role isn't to outrun it, but to understand it, to find the paths where motion already exists and use them. In orbital mechanics, this idea shows up as gravitational assists, using a planet's movement to boost a spacecraft. Instead of fighting gravity, we borrow it. Instead of building bigger engines, we use clever timing. The same principle might apply on larger scales. If we could identify gravitational flows, cosmic currents, or space-time structures that guide motion, we might use them as routes. Not highways in the traditional sense, but regions where movement is easier, where the energy cost is lower, the resistance is less, or the timing works in our favour. This isn't just hypothetical. Even now, spacecraft use natural orbital mechanics to travel. Missions to the outer planets often involve multiple flybys of Earth, Venus, Jupiter, to gain speed. It's not the shortest path in a straight line, but it's more efficient. In the future, similar principles might be applied to interstellar travel, not by brute force, but by resonance with cosmic motion. There's another way this matters. if everything is moving, Earth, the Sun, the galaxy, then the places we aim for are moving too. A star that's nearby now might be farther in a million years. A planetary system that seems reachable might drift out of alignment. The timing of journeys, then, becomes not just a matter of distance, but of trajectories. You're not shooting at a fixed target. You're navigating a dynamic web of motion. This applies to the idea of receiving messages too. If another civilization sent out a signal, it would have to know where we'll be when the signal arrives, not just in space, but in time. Our movement through the galaxy changes that constantly. If the signal travels for thousands of years, even a small miscalculation in motion can mean it misses us entirely. In that sense, our place in the cosmos is like a moving ship on a vast ocean. The sea itself shifts, the stars drift, and the currents we sail on are gravitational, geometric, and cosmological. We're not parked in space, we're adrift. And maybe, eventually, we'll find ways to steer. Some proposals suggest we could eventually build propulsion systems that align with this idea. Instead of brute acceleration, they would use the natural structures of space-time, gravitational slingshots, solar radiation, or even the push of cosmic expansion itself, to travel. These methods might take longer, but require less energy. They'd align with the universe's own flow, rather than pushing against it. In that vision, travel becomes less like launching, and more like sailing. The ship is still important. But so is the wind. So is the tide. Even our view of the night sky is shaped by motion. The constellations we see today are temporary. Over tens of thousands of years they shift. The stars move relative to one another. The patterns change. Ancient civilizations saw different skies. Future ones will too. The stars themselves are not fixed points. They orbit, they drift, they evolve. From that perspective, standing still becomes an illusion. We are always in motion, through systems, through time, through the history of the cosmos. And so, when we talk about travelling across the universe, maybe the first step is to realise we're already doing it. Slowly, steadily, invisibly. We may not have crossed light years on our own yet, but we've been carried through millions of kilometres just in the time it's taken to listen to this sentence. The universe doesn't wait for us to start moving. It moves us already. The question is not whether we'll ever travel. It's whether we'll learn to guide the journey. There's something strange about tracing all these ideas. Distances that stretch, particles that vanish and reappear, timelines that diverge, paths warped and folded, the quiet suggestion that we're never quite still. And then looking around the room you're in. Maybe it's dark, maybe you're half asleep, or lying under a blanket, or walking slowly under an open sky. And even with all of that cosmic activity happening beyond your senses, here you are, experiencing a small, consistent moment. That moment, as ordinary as it feels, is part of the universe too. And no matter how far we think we need to go, no matter how distant the stars or how impossible the speeds, we're still within the thing we want to reach. The same physics that governs galaxies governs the room around you. The same forces that pull on quasars hold you to the ground. The same light that bent around black holes is the same light that reflects gently off your hand when you move it. So what does it mean to say we want to travel across the universe? If you look at the numbers, the time it takes for light to cross from one galaxy to another, the energy it would take to bend space or survive a fall into a black hole, the engineering challenges of carrying humans safely between stars, it's easy to see a wall. Not an emotional wall, a real one. One built from entropy, probability, mass and momentum. And most of the time that wall doesn't move. Most of the time it defines the difference between curiosity and contact. But all the things we've looked at, the particles and paradoxes, the interpretations and theoretical models, the tools scientists use to understand space and time, none of them start by assuming the universe is closed off. They start by asking what's possible. They take nothing for granted. They begin from observation, and they end in math. And somewhere in between those two, The idea of unreachable things becomes part of the work itself. The boundary between here and the rest of the universe is not the edge of a planet or the skin of an atmosphere. It's not a locked door. It's a collection of limits. Some are technical, some are energetic, some are philosophical. But the point of science isn't to declare those limits permanent, it's to understand them. And once understood, some of them turn out to be flexible. The speed of light, for example, is not a barrier in the sense of a wall. It's the structure of causality itself. It tells us what can affect what and how long it takes. But within that framework, relativity allows for bending, for stretching, for changing reference frames. It allows time to slow down for travellers. It allows distance to contract. It doesn't hand us shortcuts, but it doesn't forbid movement either. It just reshapes what movement looks like. When we imagine ourselves flying across galaxies, the image is often one of sheer displacement. Being here, then being there. But maybe that's not the only kind of motion worth aiming for. Maybe the journey happens not just by leaping across distance, but by learning how distance behaves. By understanding that what feels like far away might be closer under the right conditions. That time and space aren't barriers, they're coordinates. They describe the structure. They don't decide the outcome. If that feels vague, consider this. Most of the tools we now use to understand the cosmos came from questions that didn't assume limits. Quantum mechanics didn't arise from a desire to describe small particles. It arose from trying to understand light, energy, and the failure of classical theories. Relativity wasn't written to describe black holes. It was built to reconcile motion, time, and observation. The discoveries that shape our understanding weren't designed for inspiration. They were designed for precision, and yet they inspire. Not because they offer guarantees of success, but because they widen the space of possibility. The idea that maybe we're already part of the universe we want to reach isn't meant to be a comfort. It's a fact. There is no outside in the way we sometimes imagine it. When we talk about travelling far, we're still talking about moving within the same set of physical laws. There's no other reality waiting at the end of the road, no different physics on the other side of the stars. The universe is one and we're in it now. The air you're breathing, the surface under you, the sounds you hear. All of it made from the same materials found in nebulae, stars, moons and interstellar clouds. Carbon, oxygen, hydrogen, iron. The building blocks don't change when you leave the solar system. They don't vanish when you pass a boundary. The strange thing is that we've never been separated from the rest of it, only from the view, so the challenge becomes one of perspective. When you want to explore the universe, you're not looking for something alien. You're seeking another version of what you're already part of. More light, more time, more space. And the tools we build to find it, telescopes, probes, theories, questions, are extensions of that same material. Even the thoughts that drive you to wonder where the edge is, or whether there's a way to reach it, are themselves physical events. Neurons firing, chemicals reacting, information travelling through space, just on a much smaller scale. If you zoom in far enough, the boundary between thought and motion gets fuzzy. Physics applies everywhere. So maybe the question isn't whether we can reach the universe, but whether we can recognise how far we've already come. In a few 100,000 years, a species of primates went from walking upright to measuring the background radiation left over from the Big Bang. We went from making fire to decoding the fusion processes at the core of stars, from carving symbols into stone to building satellites that orbit other planets. We haven't crossed galaxies, but we've built machines that did. Voyager 1 has left the heliosphere. It's now in interstellar space, still sending data. It didn't need to go fast, it just needed time. That's what makes progress happen in a universe this big. Patience, precision, and persistence. And even without travel, we've already seen billions of years into the past. Not metaphorically, literally. The light we collect from distant galaxies has been travelling since before Earth formed. Looking at that light is a kind of time travel, a record of what was preserved in motion. No ship needed. just a sensor and enough understanding to interpret what the data means. The desire to explore, to move outward, to discover new places is fundamental. But sometimes the universe offers depth instead of distance. Sometimes the thing worth understanding isn't where to go, but how things work right where you are. Because the structure of reality doesn't change when you move through it. It just reveals more of itself the longer you look. That's why even the smallest experiments matter. Smashing particles together at near-light speeds, cooling atoms to near absolute zero, measuring the timing of photons across vast distances. These aren't distractions from travel. They're foundations. They're how you learn the rules before you try to push them. And one day, those rules might give us ways to move through space differently, or to send information faster, or to build systems that simulate entire environments, allowing exploration without physical movement. We don't know yet. But we didn't always know the Earth orbited the Sun either. Understanding builds slowly, layer by layer. So for now, the question, can you really travel across the universe, doesn't have a simple answer. But it does have context. You're travelling already. You're spinning with a planet that orbits a star, which orbits a galaxy, which is drifting through an expanding universe. Your atoms were forged in stars that died long before Earth formed. The light that hits your eyes now has travelled unimaginable distances. And the ideas you're thinking, the ones about warp drives and time dilation and particles tunnelling across barriers, those ideas exist within the same physical universe you want to explore. That's not the end of the journey, it's part of the beginning. If you'd like to continue exploring thoughts like these, quietly, slowly, scientifically, you're always welcome to stay with us. Whether you're falling asleep, drifting in and out of focus, or simply letting your mind wander through the edges of possibility, there's more ahead. Thanks for being here with Science for Sleep. If you found this comforting, or if it gave your mind a quiet place to rest, feel free to subscribe or leave a comment telling us where you're listening from. We make these stories for curious minds and tired thoughts, to give you something steady to drift with. Wherever you are right now, and however far you feel from everything else, you're part of something vast. Sleep well, and we'll see you next time, here at Science for Sleep.